Hello and welcome back. So this is continuing the parallel computing course from TAC, and now we're going to talk about the Stampede user environment. On the syllabus, it actually said Linux user environment, but it's more appropriately referred as the actual environment that we have here for performing our tasks. My name is Antía Lamas Linares, and I'm part of the HPC group here. Okay, so just a little overview of what we're going to talk about. Essentially, we want to start you as effective users, so users that will make good use of the system, and also users that will be good citizens of the system, meaning that you won't interfere with what other people are trying to do. So we're going to talk about how you get started accessing Stampede, generally accessing TAC systems. Then we're going to give you a little bit of an overview of Stampede, what we have there, resources that we have there. What you're most interested in is probably the getting work done part. So how to submit jobs, where to submit jobs, etc. And again, this good citizenship aspect, which is how to not abuse the system and be good citizens of our systems. After this, we'll have a little lab where essentially our purpose is to get you onto the system and start playing with the tools we have there. Make sure that you can do the basics so you can go on to more complicated things. A little bit of a disclaimer here. We're assuming as an audience that you're relatively new to supercomputing. We're going for breadth rather than depth right now, just get you acquainted. And a lot of these things change, meaning that don't take what is said right now as gospel and never look again at user guides or user manuals, because things do change, the type of queues we have and so on. So it's worth actually revisiting things once in a while. For example, when new systems come online, definitely you'll have to relearn little bits and pieces, although the basics will stay current. Type of questions that we address, well, and this is not just referring to this particular tutorial, but in general, we have a help desk, which we all participate in. We help with a lot of things. We help with Linux and Unix in general, a little bit. Mostly we assume you know what you're doing, but we're there to answer questions. We help a little bit, again, with specific applications and programs, especially if there are programs that are supported in our systems, meaning they have a large number of users and some of the problems are known problems. Mostly, we help with the environment at TAC. That is, the systems in particular, how the environment is set up, interactions between systems, how do you transfer data from one system to the next, such as the Ranch archive, because all of these bits and pieces have little idiosyncrasies that you need to be aware of. And we do provide some advice about computing in general, just to get people up and running. About the Linux Unix help. The first port of call when you have a doubt about a command is to use the man pages. That stands for manual pages. So if you don't know all the options for du, disk usage, or any other command, you type man du, and it will tell you a lot of information. Normally it's too much, and the problem with that is that you need to know that the command exists, which is always the problem with Unix. If you don't know what command to search for, then you don't get anywhere. Again, there's lots of source of information about this, so it's not the type of thing that you immediately go to the help desk for. There's a lot of information online. But we're there to advise you as well. Help with specific programs. Again, mostly for programs that are supported in the TAC systems. What we mean by that typically is that these are applications or programs that are installed system-wide, and there's a module for them, and we'll get into the module system later. But if you're using something like FFTW, which is a fast Fourier transform program, there is a module for that, meaning it's installed system-wide, and you can do module help FFTW, and it will tell you a little bit more information about that particular program how to get things set up. Many times, if it's a supported program, somebody at TAC would be, and I don't want to say proficient at it because we're normally not users of the programs, but we've seen enough problems and other people dealing with the programs that we can usually help a little bit, at least point you in the right direction. Now, the most important part, help with the environment at TAC. Please have a look at the user guides. Some of them can be a little bit overwhelming, but they do contain a lot of information that can save you a lot of time going around in circles. There's some link there. Sometimes user guides, the information is there, could be not as clear as we would like, especially if you're not very experienced. So don't hesitate to ask a question if you have a doubt. We have mechanisms for that. And then there is help with computing tasks in general. And that has to do with things, and this course is particularly, this parallel computing course is particularly relevant for that. Sometimes people ask about, how can I, any suggestions about how to either debug this particular problem or how to make this more efficient. Now, people at TAC, we don't have the resources for really getting into the nitty-gritty of codes, but we can give some sort of general advice or point you into things that you should look at least. We're happy to do that. That's what we're here for. And if you have a particularly thorny problem or something that is really beyond the scope of a help desk question, there are mechanisms in Exceed, they're called ECSS projects, to request actual dedicated support. And I won't get into that, but you should be aware that those mechanisms exist. Okay, so let's get started. How do you access Stampede and in general TAC resources? So before you log in, and this hopefully you've already done, both the people that are here in the room and people that are online, you need some kind of account before you can log into any of our systems. That is obvious. There are essentially two avenues to get into TAC. There is the Exceed way to get into TAC, and there is directly interfacing with TAC systems. So if you're an Exceed user, you need to have, as a first step, an Exceed portal account. And that's at Portal Exceed. The link is there, portalexceed.org. If you're from the UT system, you should get a TAC portal account. The other thing you need, that gets you into the portals, you can see what's there. That still doesn't get you into any of our actual computing systems. The next thing you need is an allocation, meaning you need to have computing hours, actual computing resources allocated to you. Now that has to go via a project. It's not given to individuals, it's given to projects. And the only people that can ask for projects are PIs, people that qualify as PIs. So that is typically postdocs, professors, that type, not necessarily an individual graduate student. So once you have an allocation, once there's an allocation, the PI needs to add all the users that are authorized to use that allocation. And once you have that, there's a little handshake between the portal and the allocation system, and then you're authorized to get into the systems. For TAC, that can happen really quickly. Exceed typically takes a little bit longer. It has to go through a few more steps. But it's not a complicated process. Just note that the credential, some people have both Exceed credentials and TAC credentials, and they do not have to be the same. We get some people confused about this. If you can have both, but you shouldn't have more than one account in our systems. So that means you might have a different SSH name, but you're at the end of the day, everything needs to go to the same account, or should go to the same account. Okay, so this is what things look like if you actually go into the TAC user portal. For example, this is the project that we will use for this course, because every computing unit in Stampede is allocated to something. Every activity that happens in Stampede needs to be accounted in some way. So training, for example, has a particular project, TAC, HPC, local training. Our PI is sitting right there. And the important thing is that you can see some interesting details if you go to the project and you look at your allocation. There's the name, there's the PI. Very important, there's a big red arrow there. There's the Unix group that allocation, that project is associated with. That is important because when you actually send a job, you want to make sure that it requests time from the right allocation. Now, if you only have one allocation, this will happen automatically. You don't need to worry about it. But if you have several, you can get into quite a confusing situation. You run out of SUs in one project and you have all your SUs in a different project, etc. So that is worth paying attention to. There is also a little bit more information there. There's the project award and how much storage you have, and if you click around in that screen, you can find how many SUs you've used, which jobs used which SUs. There are several users of the account. You can see who used what SUs, etc. So it has really a wealth of information. Okay, how do you get into the system? Well, ideally, you start with a Linux-like terminal or equivalent connected, obviously, to the internet. You can do this in a few ways. In Linux, this is your bread and butter. There will be a terminal program there, and you can just SSH. If you're in Mac, pretty much the same. You can open a terminal, SSH will be there, and you can just log into Stampede. If you're in Windows, things get a little bit more complicated, mostly because there are lots of options. You just need to have some kind of secure shell client that you can use. There's PuTTY, there is a bunch of things. And for Exceed people, you can also access from the Exceed portal. Okay, once you have your terminal window, SSH stampede.tac.utexas.edu. That's if the username on your local machine is the same as in Stampede. You don't need to specify anything. If you have different usernames, you have to put it there explicitly, as you see in the second line. That's all for a text interface with Stampede. If you want to have a graphical interface, if you want to have an X window, meaning that you're going to plot something or in some way need the graphical output of a program, you need to do what is called an SSH tunnel. So SSH, either -X or -Y to Stampede. Now, that is something that you can only do, that's not the most common way of operating in Stampede. Most people operate in batch mode such that they do not require a graphical output, but we do have some queues that are specifically thought for that type of work. Yep. There is a difference. I think one of them sends through the different set of credentials than the other. And I forgot right now which one is which. But you have to look at exactly what you need to do and what kind of credentials you need to send over. One thing I will warn you is that we get a lot of questions about this, actually. People from the Exceed portal or that are logging from Exceed, trying to make the SSH tunneling work, and it fails sometimes. It's a little bit hard to debug when it has to go through a lot of gateways. So if you have to do work of this type, SSH tunneling, we usually recommend that you try to make a TAC portal account and go directly to the system. Makes it a little bit easier to figure out what's going on. Okay, once you log in, so you got into Stampede, that's my login screen. There's a little text blurb that comes up. It actually gives you a lot of quite interesting information. First of all, it tells you who you are. I'm A. Lamas. And then it tells you all your projects. So I'm a member of tech team of ACCSC, never mind what that is. And I should be part of the training account. Not when I took this screenshot, but now I would be, and you'll see it when you log in. The interesting thing, it tells you how many available SUs you have. You see that tech team has overrun its allocation by about 2,000 SUs. So I can't actually run jobs with that. If you see a negative number there, it's going, most likely, unless there's a count bypass, it's going to reject your job. My other project, ACCSC, actually has a ton of available SUs, so that's where I actually run all my jobs. It tells you also the expiration date. So that's that first block. Then you have your disk quotas. So you see that there's a home and a work that appear there. So home, your home quota is actually pretty limited. It's 5 gigs. It's backed up. It's very nice, but really you should reserve the use of that for, those are results, like really condensed results that you want backed up and you don't want to lose. Then there is work. Work was mentioned this morning by John Cass. That is this system called Stockyard, and several of the tax systems actually share the access to Stockyard. That is a parallel file system. You have a quota of what is it? It's 10 terabytes. No, 1 terabyte. Sorry, 1 terabyte there. So it's a fair amount of storage. It's persistent, meaning that it won't get deleted, but very important, it is not backed up. If you lose or delete something there, it's not recoverable. So it's very important that you get your results there. You can analyze. It's a great place for analyzing results, for example, or keeping stuff there that you need handy. But definitely be aware that you need to back that up yourselves. There is a third system that doesn't appear here in the quotas because you don't have a quota, and that is Scratch. It was also mentioned this morning. Scratch has essentially unlimited storage, but it's definitely not backed up. And moreover, it's not even persistent, meaning that we reserve the right to purge it. Our policy is that every 10 days, or files older than 10 days might get deleted. And there's no recourse. If it gets deleted, it's gone. So you have to be careful. It's very nice because you can really run huge simulations, put the output there, do some analysis, save some kind of condensed results to work and keep working. But Scratch is only for temporary results. Okay? So that's very important. All of these systems are Lustre file. It's a Lustre parallel file system. So, and that has its own advantages and disadvantages. So it's a huge shared file system. It works pretty well, but there are certain activities by the users, by system changes, that can make it unstable under some circumstances. So you have to be aware of that type of thing. I'll talk a little bit more about it. Okay, shells and startup scripts. So starting up, when you log into Stampede, there are quite a few things that go on in the background. First thing you need to know that our operating system is Linux. It's CentOS, actually, which is derived from Red Hat. By default, your shell is going to be the bash shell, but you can't change that, or you can't get it changed, I should say. You can't change it yourself. You need to ask us to change it for you because of how things are set up. But you just send a ticket and we'll change it within a few minutes. There are a whole bunch of script system level startup files that get executed before your own personal stuff gets loaded. And that is things like the default modules, default paths in the system, et cetera, et cetera. There's a whole roster of those things. You can set up your own customization of your environment in 2 files, essentially, .profile and .bashrc. Those are the ones that we recommend that you use. In particular, .bashrc is heavily commented. You'll see it. It has a lot of, it looks kind of complex, and the reason for the complexity is it tries to avoid conflicts between what a user can put there and things that are in the Stampede scripts. It's worth having a look and seeing where you can actually insert your own customizations. Just a word of caution there, the shell, when we talk about the environment associated with a shell, it's really associated to the one window that you've opened, meaning that if you open 2 Stampede windows and you change something in one of the windows, that won't necessarily propagate to the other window. So it's easy to get confused there. Another word of caution that we added there, because it happens often enough, is that if you put an echo in your startup scripts to see what's going on, that can break SSH. So often we see that people have changed, they started customizing their environment and then suddenly things go wrong in terms of the SSH. They're not able to log into the system or similar things. Okay, a few notes. If you're not already familiar with one of the text editors that are available in Unix systems, you should get familiar with one. You can choose, there is Nano, which is very simple but becomes cumbersome for doing complicated things. There's VI or Vim, which is very powerful but kind of obscure. And there's Emacs that is powerful and also obscure but in a different way. It's sort of choose your poison. Different people have different preferences, but you should definitely become familiar with at least one of these editors. Also, another word of caution, and it looks like this presentation is mostly about words of caution. You need to be aware, especially if you come from a Windows system, of cross-platform issues. Especially, there are a lot of hidden characters that you will not see when you're typing something, but get saved into a file and can break havoc later on. So, for example, if you save a text file in Windows, unless you're a little bit careful, things will not work well in Linux or Unix. So you have to just be aware that that can be a problem. If you're in Windows, use the simplest possible editor you can find and try to look for the option that says ASCII or text only. Another thing, if you're used to Windows, Linux file names are case sensitive. So try to be aware, don't distinguish your, be careful that files that in Windows can look the same are not the same in a Unix system. And blanks in file names require special care. I would be even more blunt than that. Do not use blank spaces in file names. It just saves you a world of trouble. There are lots of scripts, not just what you could write. You could be very careful about what you write and be sure you could deal with blank spaces in file names. But there are system scripts and so on that do not deal well with those things. And sure, maybe they should, but just don't use blank. It will save you a lot of trouble. Be careful if you use something like Microsoft Word, that probably will save things in a format that is not directly usable by a Unix system. There's a nice tool if you're not sure how a file was saved. Use something called DOS to Unix utility. You can type DOS to Unix, initial file name, destination file name, and that will sort out a lot of the issues, cross-platform issues. Okay. A little bit of a tour. I think this overlaps a fair amount with what John said this morning, so I'm going to sort of whiz through. A Stampede node, a blade, is essentially a Dell PowerEdge 8220. That doesn't really tell you anything, but that's the typical compute node, and there are thousands of these. So this is what it typically looks like. There's a host, and that's the main processor. Essentially, we have 2 sockets, 8 cores each. And then there is a coprocessor, what we call the mic, the PHY, which has 61 very lightweight cores and 8 gigabytes of RAM. So that's your typical Stampede node. You have 16 cores of a normal, similar to a desktop processor, and then 61 of these very light mic processors with a lot less memory, but other characteristics. And it needs, these things need a little bit of special care to use because it's not instantaneously obvious. And that's what you'll learn later on. Basic specs of Stampede. As I said, we have like 6,400 blades in 160 racks. Your typical node has 16 cores with 32 gigs of RAM, and the mic processor, it's 61 of them with 80 gigs of shared RAM. Then there's some specialized nodes, and those, the way you find or why you should care about the specialized nodes is that there's special queues that you can submit your jobs to if you need special hardware capabilities. So there's 16 large memory nodes. The important thing there is they have 1 terabyte of RAM. That is a lot of RAM. You can build a RAM disk. You can do things that you can't do in other places. There are 128 GPU nodes where you can use this the NVIDIA card to do some computations. They also have a mic. And then very important, there are 4 dedicated nodes that are just for logging. So when you actually log onto Stampede, you don't arrive into a compute node. You arrive into a logging node, and these nodes are special. I'll talk a little bit more about them. So that's a graphical representation. You have your logging node, that's where you arrive. That's where you compile your code, and that's where you submit your jobs. But by submitting, we need something very specific. You're submitting to a queue. You're not running there. Okay. So what does it mean? It means that you really should not be executing any of your code on the login node. So when you just arrive to Stampede, you have a program. You don't just type the program and run. That might work for a little while until our system admin realizes, and then he'll go and kill you and ban you from the system, essentially. That's every day we have 2 or 3 people that said, I cannot log in, I'm banned from the system, what happened? And that's the reason. Mostly it's just an error. I mean, people are not trying to be nasty, but we have to be very strict about this. The reason is, as I said, there are only 4 of these login nodes, and there are hundreds and hundreds of users. If you run a heavy job on the login node, other people cannot log in and they cannot submit jobs. So what you need to do is submit a batch job. That's what we're going to talk about in a little while. So I already mentioned this, that you have 3 file systems, the home, work, and scratch. They each have aliases. So you can get to home by $home, to work by $work, and to scratch by $scratch. You can always use these names to refer to these different partitions. And you should use them. You should acquaint yourself with what is the best use of each of these systems. We have a little shortcuts for how to get there. CDH is CDs to home, CDW CDs to work, and CDS CDs to scratch. One little caveat is that if you get into the mic coprocessors, you can see the file system, but all of these aliases and a lot of other things do not work if you are in the mic itself, if you SSH to the mic coprocessor. The reason is that the mic runs a very stripped down operating system itself, and there's very little that is built in. It's a very bare bones system. There are other tools to deal with that. Okay, how do you get your files or your stuff into Stampede, into your account? Well, the easiest thing is using Secure Copy, SCP, rsync, or the Exceed tool, Globus Online, and there's some other protocols. Personally, I would recommend, if it's a single file or just a few files, use SCP. It's very easy, it works very well. If you have a lot of files or big files, use rsync. rsync works the same way as SCP, but if for whatever reason the transfer gets interrupted, it will pick up where it left. You can just rerun the command and it will pick up where it left. It doesn't have to start all over again. The bandwidth into all our systems is somewhat limited, so this can save you quite a bit of time. Now, next point is a little caveat about parallel file systems. So One of the things that really stresses the parallel file systems is querying it about the status of files. And it's very counterintuitive, but if you use some of the Unix commands with recursive flags, this can, especially if you do it from a very high level directory, this can really stress the file system, because what is happening is that you're querying the metadata server, which is what tells the rest of the file system what exists, over and over and over. And again, there's just a few metadata servers used by every single process in Stampede. So be aware of that, also within your programs. These file transfers, you can and should do them from the login nodes, but do not start 10 parallel transfers. Again, this is the type of thing that our system admins will see. It's like, okay, this person is stressing the login node, out. And they'll kick you out. So, limit your commands that you are simultaneously running in the login nodes to a couple of processes. Maybe you start 2 rsyncs or something like that. 2 is fine, and a compilation, something like that. 10 is not, because it will affect other people. Usually you don't need to compress and optimize manually what you're doing for these purposes, with one exception. And I'm talking about moving stuff from, say, your desktop to Stampede. John mentioned this morning that we have a tape archival system. It's called Ranch. Now, Ranch works in a little bit different way than all the other systems, because it's literally uses big old tapes to store your data. Those tapes have to be, if you store data, it has a little bank of hard drives that the data gets put there first, then it gets written to a tape. But there's literally a robotic arm that goes and takes a tape, and data gets written to it, and then it gets stored away. So it takes special care especially to take data out of Ranch. When you want to take data out of Ranch, you need to stage it first. That means copying it to the local hard drive first, and then transferring it out. It's described in the Ranch user guide, but it's worth being aware of that. Sometimes people are like, I just tried to get my 20 terabytes out of Ranch, and it's giving me all these errors, and then there are all sorts of problems. So that is a very special system. Okay. Getting work done using Stampede. So I mentioned before modules. Modules are a way that we use in high-performance computing to set up your environment depending on what you're going to use. So this is not like your workstation where you have installed whatever you need and you just have your paths and everything set up. What happens in Stampede and other high-performance computing systems is that you tell the system what you're going to use, and it will dynamically set up an environment for you. That means the paths to the libraries, the paths to the executables, sort out dependencies, and so on. In tech, we use a module system called LMOD. And it's worth familiarizing yourself a little bit with LMOD. Why do we need such a complex thing? Well, the reason is that we have multiple compilers installed, and this will become important for running parallel jobs. And we have multiple MPI stacks. So we have, for example, we have the typical GCC compiler, we have an Intel compiler, and then we have MPI stacks. We have the Intel MPI, and we have MBAPICH. And you need all the possible combinations of those things to run your software. I mean, you don't need all of them to run your software. You need to know which one you want to use to compile your software, and then use the same one to run it. So it's important that those things are consistent. Just a note there, it says modules can affect the mic operations, definitely. But again, the operating system within the mic itself is not available. The operating system within the mic itself is very simple, very stripped down. The modules are not available there. You have to do it externally, and then it affects how you run things on the mic. So some key module commands there. Module help tells you a little bit of how to use it. Very important. Module load X. So for example, module load FFTW3, it will load something. Module avail, short for available, will tell you what modules are there for you to load. Module unload, whatever, when you want to get rid of it. Module swap, say that you loaded Intel 13 and then you realize that you actually want to use Intel 15. You do module swap Intel 13, Intel 15, and it will change everything for you. Module spider, this is very useful. When you want to know whether a particular software is installed in Stampede, for example, PETSI, it says there. So module spider PETSI will tell you all modules that have PETSI in its name. And you might find that there are multiple versions of the software you want to use. You have to decide which one you want to use. ML is short for module list. Again, very useful thing before you run anything to do a list of the modules that you have loaded so you know what your environment is. That is particularly important if you run into issues, because we're going to ask you, what modules did you have loaded? And module reset will take you back to the default in the system. You can also customize your modules by making sort of a package of modules that you usually use. I'm not going to go much into that. There's several ways of doing that, but there is a mechanism within the module system itself to save a bunch of modules. There it gives an example, module save chem tools, and that way you always have it available. Okay, compilers. A word about compilers. So, and this is a little bit out of date as of a couple of weeks ago. So it says there, Intel 13 is the compiler of choice for Stampede. As of now, Intel 13 indeed is the default compiler in Stampede. If you just compile your code, that's the compiler that will get used. Now we just installed and we're moving towards Intel 15. So if you're going to start programming or compiling programs right now, I suggest start already with Intel 15, and that way you don't have to migrate later on. So, you know, once you start doing your own work in Stampede, go in, say module load Intel 15, and that way you'll have that one available. I think maybe in about a month or this summer, we're planning to really make Intel 15 the default, I believe. Is that right? Intel 15 will become the default in a few months?
Yeah, a few weeks, I don't know.
Few weeks, so soon. It's worth already doing that. Now, where are the compilers, maybe surprisingly, are not available everywhere in Stampede. They are where in the login nodes, because that's typically where you compile, and they are available in the development queue. So there are a few nodes that are reserved for development, and there you have your compilers. If you try to compile in a compute node, that will very likely fail because you won't necessarily find what you need. Again, the compilers are not visible from the mic coprocessors, but it's possible to compile for the mic from the host, so that's not a problem. Other things that are important, math libraries that are used by many programs, such as MKLs or PETSI, etc. We have some information about standard things that are available. Okay, compiling for MPI, you'll get into a lot more detail of this, but essentially you see there a list of our MPI compilers. You have a MPI compiler for C, for C++, for Fortran 77, and for Fortran 90. So how do you get to the compute nodes? So how do you actually get your jobs in there? So there are a couple of ways, which are variations of essentially the main mechanism. So first thing is Slurm is our scheduler. It is what decides what runs when and where. So when you submit a job, what you're doing is submitting a request to Slurm to schedule your job. That's what you're doing. And there's a particular format of how to send that request. It's called an S-batch job. We'll have a look at one in a moment. That's the usual way people run. When you have a production code, you want to submit a job, you submit an S-batch thing. There's another way. Typically, when you're starting to learn a program or you're developing something, you might want to run interactively in a similar way that you do in your own machine. Or say you want to run a small job, do a quick sanity check that things are working as you expect, and continue working. That is quite cumbersome to do as a batch job because you send it to a schedule, then you have to wait. So there is another mechanism. And there are two ways of doing it, but I highly recommend one in particular. There's a tool called iDev. And what that does, it essentially sends a request to the scheduler for you. It says, I need a node. I want a node for myself to just work on it. So if you just type iDev in your Stampede terminal, it will submit this request. And we'll go through it later on. But essentially, it will wait for a little while until it finds a free node. And then it'll say, okay, you have this node. And there are several flags you can give it. You can ask for a particular amount of time. You can ask for more than one node if you want to test a little parallel job. And you can also tell iDev to charge that time to different projects. There are a whole bunch of flags. But as a tool, it's incredibly useful. Okay, so actually I have a little slide there about iDev. So you just type iDev, and you see it goes through a whole bunch of checks. Verifying build, submit host, blah, 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 blah. And after a while, it says submitted batch job and a number. That's your request to get a node. After a little while, indeed, it ends up with a prompt. And you'll see that prompt has different letters at the beginning, including a C and a bunch of numbers. That tells you exactly which compute node you're working on. That's interesting because you might want to run something and SSH to that compute node and have a look at what's happening in terms of memory or whatever parameter you want to debug or have a look at. Yeah, the note there is just a reminder that not all compute nodes are created equal. And with the iDev tool, you can request different types of nodes. So you might want to do a test in the development queue where you have compilers, or you might want to do a test in the GPU queue where you have access to a graphics card. Okay? Okay, Slurm. How do you submit an actual batch job? This is the production mode of work. So the command would be sbatch and the name of the script that you wrote. Yeah, and just, yeah, the second point about launching a one node interactive session, that does the same thing as an iDev. I recommend you use iDev for simplicity. Now, say you submitted your batch job, you want to look at where it is in the queue and what other similar jobs are in the queue. You can have a look by typing sq -u user ID, and you'll see what's there. There's also another command, show queue -u. They give you more or less the same information, slight differences. If you submitted a job, you realize you made an error, you want to cancel it, command scancel job ID. And you can look at all sorts of parameters about the queues using sinfo. That's a particular example there. But if you man sinfo or if you Google sinfo, you'll find you can ask for a million different things about the queue status. Okay, this is really important. What queues do we have and how are they used? Okay, so you see there's a whole bunch of names there. Normal queue. This is the one where most people run, where your ordinary jobs usually go. This has a lot of nodes available, and you can submit up to 50 jobs in the queue. So you can really submit quite a lot of things to wait there to be executed. When you submit a job, you also request for what is called a wall time. That means the maximum amount of time that your job is expected to take. That wall time is actually important to specify correctly, because if you submit too short a wall time and the time comes and your job hasn't finished, it will be killed and you lose those computation hours. If you haven't saved intermediate results, you lose that part of your work. Now, that doesn't mean you should always request the maximum allowed wall time, because the longer the job, the harder it is to schedule, the harder it is to fit in the whole, among all the other jobs in Stampede. So you want to become familiar with roughly how much time your job takes, get a good estimate, and adjust that with a little margin, or whatever margin you're comfortable with. One of the nice things about the way we charge SUs here is that we charge for actual time running and not for the wall time you specified. So, keep all these things in mind. Okay, so in that normal queue, you can run your jobs up to 48 hours. That's two days. Now, we often get requests, I want to run for a week. My job takes a week. Unless there's a special set of circumstances, we don't like that, because first of all, you should try to always write your code such that you save intermediate results every few hours, because a system like Stampede and shared file systems, they go down sometimes, and we cannot guarantee a system stable for 7 days or 15 days. That's not very realistic. So keep that in mind. Our policy is that we don't refund more than 8 hours if the system goes down and kills your job. So, it's worth writing things such that you try to save at least every 8 hours of computation. Okay, but 2 days, that's not too bad. Maximum number of nodes that you can use in that queue is 256. That's 4,000 cores. Now, there are jobs that require more than that, and that is what we call the large queue. Now, the large queue, you cannot just submit to the large queue. You need to ask for permission to submit to the large queue, because we need to see proof that you can run at scale before we let you loose on Stampede, essentially. Okay, so what are the queues? Normal. Then there's development. Development has a maximum time of 2 hours, because you're supposed to be doing kind of fast turnaround work there. You can ask for a maximum of 16 nodes, only one job at a time. Large memory, those are a few nodes that have 1 terabyte of memory. You don't need special permission to run there. You can just go ahead. One thing you should know is that those nodes are charged at double the rate, because it's a lot of memory. It's very expensive. Serial is for essentially serial jobs, so you're not doing parallel stuff. 12 hours maximum. Large queue, 24 hours. If you're running with something near to the full system or a large fraction of the system, you better be saving some kind of results. Okay, normal mic. So that is the queue where you run codes that are specifically written for mic. Now, those are physically the same nodes as the normal queue, but there's a slightly different set of tools, and the environment is set up in a different way. Normal 2 mic, there's a smaller number of nodes that have 2 mics. There are actually not that many codes that can take advantage of 2 mics, but there's some. Then there's GPU development, and VIS. All of these queues have special hardware. We really encourage you to only use the special hardware tools if you have special hardware requirements, because that's what they're there for. So if you're not going to use GPUs, do not use that queue, okay? Okay, so now there's an example here of a basic Slurm script. They're fairly simple. There are a bunch of commands related to how you set up the job. They're all preceded by a hash sbatch keyword. So you have something to set up the job name, where the standard out goes, where the standard error goes, -p option to set the queue that you want to send to. So there it's development, but it say usually would be normal or normal mic, depending what you're doing, GPU. Capital N is the number of nodes that you want. Small n is the number of MPI tasks if you're using MPI. Minus T is how much wall time you need. Then there's some other additional things to have the job email you when it finishes or when it starts. And the project you want to charge things to, that's the minus A option. And you can even add, you can even load modules within this batch script. There are advantages and disadvantages to that. Finally, the last line, that's the important line, is the name of your executable. Or if it's an MPI job, you need to run it through something called IB run. Now, if you have used MPI before, you might have come across MPI run or srun. Those don't work as such in Stampede. You have to use them via this wrapper called IB run. So where in other places you would do MPI run, you just do IB run. Okay? Other software that is in Stampede by default, and this is always changing, always under construction. There's things like R, Octave, linear algebra libraries like PETSI, Python and Python modules such as SciPy, Matplotlib, analysis and debugging. This is particularly important for parallel jobs. Parameter studies, file I/O libraries. If you do parallel I/O, HDF5, lots of different things. You can find out what's available by looking around and looking at our documentation. If you find that you need to use something that is not in the system, this is very important. So typically, if it's a one-off request, so one user asks, hey, I want to run whatever, and it's not in the system, we usually will not install it system-wide. But you can install it in your own account, and we can give you a hand with that. So you need to use the latest version or the development version of, say, Octave, I don't know. We will not typically install a development version system-wide. That's because we like our software stable. But you can install it in your own account, and we can give you a hand. One useful thing to do, so often we get people that have started messing with SSH keys or played with their environment a little bit too much and things are not quite working. We have this very nice tool called Sanity Tool. So you can load it using module load Sanity Tool and then say sanity check -v. And it will go through a few things that checks that your environment makes sense and that in principle you should be able to run things. At the end, if everything went well, it says all tests passed, and you know that at least that part, there isn't anything that is horribly wrong instantaneously. Okay. A few reminders. Again, I think I mentioned this every 10 minutes or so, but good citizenship in Stampede. Remember, you're sharing resources, so no running in the login nodes. Be aware of the file system limitations. So especially if you write a parallel program that is over, say, 100 nodes, and you have each of them querying the file system many times a second, you can easily bring down a metadata server. So be aware of your I/O. Make sure you don't unnecessarily ping files or read files, open and close file multiple times without the need. If you don't need to do it, don't do it, because things can go wrong quickly at scale. Use components for intended purposes, meaning, again, don't use the hardware, special hardware queues if you don't need them, things like that, common sense. Okay, so this is login nodes. What makes sense to do there? It makes sense to build software, to manage files, submit jobs, monitor things, launch interactive session, a little bit of post-processing. If you need to have a quick look at something with nuplot or something light, that's okay. But do not run a job there. So inappropriate use, yeah. Do not do science on the front end. And do not do a lot of things of allowable things, meaning don't compile software, a huge package using all the available cores, things like that, because that's going to affect other people. Don't run 10 rsyncs at the same time. File system awareness. Home. Home is where you arrive when you log in if you don't change. Don't run jobs from home. Don't write your input, your output into home if you can possibly avoid it. If you can, run things from scratch, then move the data over, either to work or to home, depending on what your needs are. I already said this, avoid frequent I/O if possible, avoid simultaneous I/O. And you might, there are lots of things that are not obvious, but you might have to learn to recognize other stressors on the file system, recursive things, etc. Okay, and I think that's about as much as I want to say for the general introduction to the environment of Stampede. Let's do a quick break and we can continue with the lab in a few minutes. Yeah? Oh, from Lone Star to Stampede, you can use SCP, secure copy. So assuming you have accounts in both, right? So you're in Lone Star, you can just do scp stampede.tech.utexas. Yeah, so scp blah, blah, blah. And then you need to put a column and that will transfer it and then the directory where you want it. So it's like a copy, it's like a CP. I can give you an example. Uh-huh. You can show me, I can tell you. Yeah. I'm not sure I understand. So it's not interconnected, so I have to check with my mom. Yeah, you have, yeah, you don't have access to the same place. Although, it's interesting, although the work directory is part of Stockyard, and it's the same kind of file system, your work directory from Stampede and your work directory from Lone Star is not the same thing. So you do have to transfer from one to the other. Your quotas are also independent.
You can transfer files directly from the Stampede shares.
Yeah. Yeah, it's a little bit confusing because some systems do share and some don't. Yeah. Yeah, let's start in 10 minutes with a lab. let me know when we're okay. So after that brief break, let's just get finally log on to the system and just have a look around. We'll just make sure that you guys can log in and we can try some of the things we discussed. Okay, so does everybody have a terminal open? In the room at least? Okay, so let's try to SSH. Let's just follow along. So I'm going to SSH into my account. So this is the first time I log on this computer, so I need to accept that. And all right, so I'm in the system. And I just want to go at the beginning. So you can tell this is what I was showing you before. It gives you a little bit of information about what's going on in my account. So let's see. First, it has some tips about the system or some rather general usage things. And then finally, it gets to project balances for user llamas. You see my projects up in the screen. You see the TAC team with a negative balance, the ACCSC, and you see a new one, training HPC. That's what we're doing right now. And that's the one that you should all have as well. You might have some other one if you're a member of a project, but at the very least, you should have that one. After that, you'll see a tip, and that's actually a tip. There's a module that loads tips. Those are useful tidbits of information. It's worth reading it. Usually, you read them for the first 10 times you log into Stampede, and then you get too busy. All right. Now, we have 2 allocations associated with this course, one for TAC people, that's the training HPC, and if you come from Exceed, it will have a different name. I think it's the one that's there on the screen, the TG, TRA, etc. Okay, so let's get started. So we already logged in. Why don't we try to go onto your workspace so that the shortcut is CDW. CDW. And let's do PWD. That tells us where we are. So in my case, I'm at work, 0 some number, and then A llamas. That's me. And the first thing we need to do is get the examples file that the lab is based on. Okay, so what you need to do is, it's on the screen, on the slide, it's tar xvf minus, or rather, sorry, tilde, train 00 / stampede _ user _ m _ lab. There you go, short name. And once you have that, just press enter, and that will unpack, will create a new directory in your workspace with a bunch of new files and a README file. Okay, so I'm going to look at my directory with ls. There's a new directory called Stampede User Environment Lab, and I'm going to cd into that. Stampede User Environment Lab. There we go. I do ls again to see what's there. And you see a number of files. In my case, I have more files than what you probably have because I had already opened this before. Let me make this screen a little bit more reasonable. So it fits here in R. Okay, everybody in the room has the lab files? All right. Okay, so first thing we're going to do, let's start by Let's do a module list first. Type module list. Let's see what modules we have here by default. Module space list. So you see currently loaded modules, TAC paths, Linux cluster paths, Intel 13, that's our default compiler, MBAPICH 2, that's the default MPI stack, and some other things. And among them, you see Sanity tool. Okay, so now it's loaded by default. Actually, we don't need to load it, but we can do it anyway. Let's do module load Sanity tool. Still happy, okay. And let's do sanity check. So sanity check is something that you do in your own account. So you just type sanity check and -v for verbose. So it tells us all sorts of things. There we go. Okay, so you see there the different things it does. It says SSH permission test passed, SSH key test passed, standard variables, file system availability passed. Are we blocked? Has one of the admins gotten really annoyed at us and said you can't run things? No, we passed. Our quotas are fine, the module environment is fine, compilers are fine, and the scheduler is fine. All tests passed, we're good to go. At least, you know, it's a sanity check. It's not a guarantee. If one of you, by the way, if you get a non-pass, let me know, because something we'll have to fix that. So one of the very important things about sanity check is that it checks your SSH environment. Without a properly set SSH environment, your parallel programs will not work. So that's pretty critical. Okay. We already did some module list. You can play around. We can do, for example, let's do module spider Intel, for example. Let's see what Intel compilers are available. Okay, so you see there are a whole bunch of them there. There's actually more than one Intel 13, although only one of them is the default. And then there's an Intel 14 and an Intel 15. If we wanted some more information about one of these modules, we can type module spider Intel, let's say Intel 15. And we can use tab autocomplete here as well. Okay, so there comes up a more detailed description of that module. It tells you, where it comes from, the type of things it can be used with, and very important, the type of paths that it sets up in your environment. The ICC lib, ICC bin, etc. In any case, it's worth knowing that you can get more information about a module by just doing that. Okay, that's fine. If you played with some modules and want to get back to the system defaults, module reset, it's a nice way to just make sure you don't have anything strange loaded up. So module reset, resetting modules to system default. We're back to standard, yeah? Okay, so when you change a module like we're doing now, that does not persist. That is just for this session. It's just for that one session. If you want something more permanent, you have several options. You can put modules in your bashrc file. There's a place to load modules there. As I said, that file is heavily commented, so it will tell you this is a good place to put modules. And you can load them there. Say you always use, FFTW or whatever, or you always want to use the Intel 15 compiler, for example. You can just load it there, and that way you forget. You don't need to think about it. Other solution, I mentioned it briefly in the previous section, is in the modules itself. You can do a module save you load a bunch of modules, and then you want to save that collection of modules into like one group. You can do module save something, and to get it back, you just need to do, I think it's module restore. So there's more than one way to do it, and different people have different preferences. But it's not it's not persistent. If you just load things up, it won't stay. Next time you log in, you're back to a 0. Huh? You can save a default. That's right. And that's another way. So again, there's more than one way, which is a reason why it's a good practice to have a list or an echo of your module list before you run a big job. Make sure you know what was loaded, especially if you have anything complicated. Okay? Okay, here we go. So let's look at an MPI batch job. So this is just to, this is not a course on how to run MPI or anything, but let's just play around a little bit so you can see how things go. Okay, so we are in a login node. You can see that actually because that prompt in your terminal doesn't say whatever C and a bunch of numbers. This is a login node. It probably says Stampede 2 or Stampede 3, something like that. I'm not sure. It depends on your environment. I think I have mine customized. Okay, so we're in a login node. We can compile here, right? So let's look at the programs you have in that directory that we just created from that tar file. And there should be an mpi.pi.c. Do you have that there? Okay, so let's compile this with the default compiler. So mpi.cc, mpi.pi.c minus o mpi.pi. Okay, so that was quick. It compiled. And now you should see an executable in that directory. So I'm going to look at the files with all the permissions. There it is. So there is an MPI.pi that's created on May 4th and has execute permissions for the user. Okay. So you have now an executable program. Now we want to run it. Okay, so let's open up the sbatch. We have an sbatch file there called mybatch. So let's open it up. I'm going to use nano because it's really easy. So nano mybatch. Let's open it up there. Okay, so here we see the actual structure of a batch job to submit to Slurm. Okay, first thing, hashbang bin bash. That's just the shell. There's some commented out things there, JavaScript for Stampede Tour. That's just something that does nothing. D. James is Doug this morning gave the introduction. He wrote this script originally. Okay, and then come the actual sbatch command. So sbatch minus j. That's the name we're going to give to our job, MPI.pi. We just named it the same thing as the executable. It could have been something else. Okay, sbatch minus O tells you where do we want the standard output to go. And that's the name of a file and a modifier called that is a %j.out. That %j expands to the job number once that thing has been scheduled by the scheduler. So it's really nice. Later on, you go, you look, you know exactly which job number created what output. So you have the standard output, the -c gives you the standard error, -p gives you the queue. Here we're submitting to development. Then capital N number of nodes, little n number of MPI tasks. There's a default little n equal big N if nothing is there. And we have maximum time, maximum wall time. I put 5 minutes there. Finally, we have the allocation that we want to run this under, and that's training HPC. Okay? Forget about the other 2 lines. Last line is the important thing. IB run. This is running an MPI job. and the name of the executable, and it has some parameter, which in this case is 200,000. Never mind what that means. It's not important. Okay, so let's get out of here by doing Control X, and let's run that. Okay, so we do sbatch, my batch. And this will submit this to the queue. Okay. Okay, so it starts submitting things. Once it says that it's submitted, we can try to have a look at what the status is in the queue. So it does a full set of little checks. Still working on it. Checking available allocation, submitted batch job number, blah, blah, blah. Okay, so now let's do SQ minus U. I want to see how my job is doing, right? A lemmas. You put your own username, obviously. Okay, so there it is. It says job ID is whatever, partition, that's the queue, is development, that's the name. User status is pending, so it's still waiting to run. Time it has run 0 because, well, it hasn't run. And I asked for 2 nodes. I can do it again, and it's running now. Shouldn't take very long. Okay, takes a few seconds. Have you all been able to see your job? Is it all running? Oh, come on. Is it done? Okay, well, let's see if we can continue anyway. Sorry? No, this is not an IDEF. This is an SBatch. This is a submission to Slurm. This is what usually happens, right? You submit and then it has to wait. I'm surprised that it hasn't run yet. Is it? Oh, okay. Yeah, okay. Yeah, okay. So there we go. It's completed. I was looking above to the R. Okay. So we have there you should have an output that has in the name the actual job number that you got before. Okay, so let's have a quick look at that output. Let's do less. That will just show things. Less dot whatever your job number was. The standard out. And it says a little thing. It says starting job whatever, setting up parallel environment, blah, blah, blah. And it has a computed value. MPI pi was obviously computing the value of pi. Gives you some error. It gives you a few things. And then it exits. So this is a little sample program. Nothing special about it. Okay. Now let's run it. So that would be how you submit a job. You have an executable, MPI executable. That's how you submit a job. Very simple. Let's say we actually want to do things interactively, run short versions and have a look. Let's run an IDEV session. Okay. So first of all, let's compile our code again. Let's compile with Fortran, an OpenMP version, and a non-OpenMP version. Okay, so ifort minus OpenMP, that's the flag that tells us to compile with OpenMP, and hello F90, that's what the program is called, minus O hello 1. So let's compile that. Should only take a moment. And let's do also a version that doesn't have OpenMP. All right, so we have now our executables. Now let's run an IDEV session. So that means we're going to ask the scheduler to give us a node for our own use. So there we can run interactively and have a look at things. So IDEV minus capital A training minus HPC. Now, if you only have this allocation, you don't need to specify the minus A training HPC, but I have several, so I want to run in this one. Okay, so IDEV just started going through things and says, hey, we found an active reservation request for you named tech training. That reservation, you usually wouldn't have such a thing. That happens because for this course, we've actually reserved a bunch of nodes for our own use so you guys can run things a little bit faster. So it tells me, do I want to use this reservation? Yes. So say yes. Normally, you wouldn't get that question. You would just use your account, your allocation, whatever you specified. Okay, now it went through some checks, and now it says job status pending, so it still doesn't have a node for me. Pending, pending. So are you all pending for a node? Okay, it says job is now running on master node C401-002. That's the compute node I have. Okay, so now I have my prompt for this node. Let's run the code. We can run hello 1. And it says hello from the Sandy Bridge host. So this is running on the host. The value of OpenMP OMP get number processors is 16. That's how many cores there are in that host. And the value of OMP get max threads is 1. That's just some values that you get from OpenMP. I'm not going to go into OpenMP at all. That's something for later, but you see what's going on there. Let's run the other program, hello 2. And it just says hello from the Sandy Bridge host. This is just running no OpenMP. It's just a normal serial program. Now, a little bit of a subtlety for OpenMP. So we didn't set up any number of threads or anything like that. So our next task is going to set up the number of OpenMP threads. So we're going to do export OMP, whoops, that's wrong, OMP _ num threads. Oh, I think we're running out of time anyway. Equal 4. So export variable, whatever. By the way, this export command is what you use in Bash. If you're using C shell or some other shell, you would need to modify accordingly. Okay, 4. And we can run again. So hello 1. And say, hey, value of processors is the same. You cannot change that. That's a hardware thing. But the number of threads, you can. So you can do these things. I think we had an official break. There's only a couple of slides, a couple of things more left to do. So let's proceed. Okay. So a subtlety. I'm now this is easy to forget. I asked for an IDEV session. I'm in a compute node, and now I want to continue, right? And I would go ifort, I want to compile my next thing. Minus MIC minus OpenMP hello F90 minus O hello .mic. And it says, oops, hey, all these errors popped out. What happened? Well, I'm not in a logging node. These nodes might not have all the libraries necessary for compilation, even if things might not be available. So here what happened is it says, hey, error, a license for whatever is not available. So the license server doesn't work from this compute node. So what we need to do is exit to a login node, compile the program, get back into an IDEV session, and run. Or typically what you would have is two windows open, one in the login node. You compile whatever you need, and then you run in your IDEV session. We're running out of time, so I don't want to log out. I just want to maybe walk you through this. You can do it yourself later on. So what we were going to do is just run a mic processor, and the program was going to report how many processors it sees, which is going to be 244 because there are 61 mics, and each of them can run 4 hardware threads. I don't know if you remember the slide from this morning that mentioned that. And just warn you, if you go through this, that there is a typo on this last part of the slide. This export MIG environment prefix equal mic. This is from somewhere else. Doesn't make sense in this context. One more thing, just let you know. So you can actually, if you're in a compute node, you can actually SSH into the mic to do things. But there are a couple of caveats. The mic has a very, very stripped down operating system. So if you try to do CDW, it will not work. Things like that. All your environment variables will not be there. And you need special care to deal with that. You'll get told a lot about that later on today and tomorrow. But just something to be aware of. It's not a full operating system like you have in the host. Okay, and with that, we're going to end this very brief introductory lab. Thank you.
Go ahead and turn off your camera.
Camera and mic. Mic 2, right?
I'll turn your mic back on when you're ready to go.
We're good to start? Can we get
Yeah,
started?
you're good to go.
Hello everyone, my name is Ritu Arora and I work here at TAC, and today I'll be giving you an introduction to MPI. So with this, the objective is to just introduce you to the very basics of MPI programming. So if you already know about MPI programming a bit, you might not get much out of this session because it's really introductory level. So I'm going to share information about how to run MPI programs on Stampede, and I'm assuming that you know C or Fortran, one of those programming languages at least, to take benefit of this session. And I also hope that if you do not have access to Stampede yet, then you have access to some other MPI installation somewhere in order to do the hands-on exercises if you are staying with us till the end. So we will go over the basic concepts related to MPI. I'll talk about environment management MPI routines, which are really the bread and butter of writing an MPI program. And I'll talk about how to compile and run MPI programs. And I'll discuss briefly some API for point-to-point communication and collective communication. I will show you a few examples, and then we will be doing the hands-on session in which you will have time to do 2 to 3 exercises. Now, how many people are Fortran users? None? Okay, that's good. Online, are there any Fortran programmers?
Oh, that's
So if there are Fortran programmers, you might want to switch to slides 66 to 70 towards the end of the presentation deck in order to follow with me with the examples that I will be presenting. So I will be presenting C examples up front, and for the corresponding Fortran examples, please switch to slides 66 to 70. So message passing interface, or MPI for short, is a standard or a specification, if you will, for writing message passing library programs. And these are typically meant to be run on distributed memory architectures, but they can as well be run on shared memory architectures or hybrid architectures. However, the programming model per se is distributed memory. Okay, I hope that you have already been introduced to the various programming models in the previous session, and you already know that for distributed memory programming, you would need a message passing library like MPI, and the primary reason for that is each process has its own address space. So what you're wanting to do is do the computation on one or maybe few processes, and then let them communicate with each other to exchange the results so that you can get a global value or a global result at the end. So that's the whole point of having a message passing library like this. And note that it's not any IEEE or ISO standard, but MPI has today become a de facto standard for writing message passing programs. And it's been developed with the help of MPI Forum, which has more than 40 organizations as its members. So currently, we are at MPI 3 stage. Okay. Currently, we are at MPI 3 level. The whole effort with MPI started in early 90s, and that's just to give you a brief history that we have come a long way in these 20-25 years. And now we are at MPI 3 standard. So if you look at the latest specifications, you would know that C++ bindings have been deprecated. So the current implementations or the latest versions conforming to the MPI 3 standard would have only C and Fortran bindings. And the Fortran bindings are available for both 2003 and 2008 versions of Fortran. So as I was telling you that MPI is most suitable for writing programs for distributed memory architectures or shared memory architectures, but having distributed memory paradigm. So typically, you would have, if you will, if you take note of this diagram here, you would have multiple processes, and you will have a big chunk of tasks that you want to divide and spread it across multiple processes for doing individual computations. And in the end, you would combine the results of individual computations to arrive at your final result. So it's just like computing the sum of first 100 numbers, wherein you have got 2 people to do the computation. So you can evenly divide or distribute the work amongst 2 people. So first, you can say, first person, you compute the sum of first 50 numbers, and the second person, you compute the sum of the last 50 numbers. So that way you have split the work amongst 2 people of computing 100 numbers, right? And in the end, you can combine their local sums to arrive at a global sum, right? Similar is the paradigm with MPI. So in this diagram, you would see that this message passing interface layer sits on top of the interconnect. So, and that's the fabric that would help you communicate across the nodes. So there are basically, at a very coarse-grained level, 2 broad categories of writing parallel programs. One is the explicit parallel programming paradigm, and the other is implicit parallel programming paradigm. When you talk about languages like UPC, for example, or Fortran, for example, those are the examples of implicit programming languages wherein the parallel programming is a part of the programming constructs as itself, right? Whatever you want to achieve in parallel, you'll have a construct to help you achieve that. Wherein, in explicit parallelization, the onus is on the programmer to pick the right call to do their parallelization. So everything is explicit, right from distribution of the data to synchronization of the messages, or to, for example, coordination amongst different processes. Everything is very explicit, and that is something that the programmer needs to handle at his or her level. That is why it's called explicit parallelization model. So typically, you would when I say typically, I would say typically I would write a parallel program with MPI paradigm like this. I would first have a working sequential application that I would then profile and see if there are any bottlenecks or if there are any places which are consuming a lot of time. And after I get my profiling report, I would want to focus on which areas do I want to parallelize, and are there any hotspots for parallelization. Once I've identified the concurrency or any hotspots for parallelization in my sequential application, that's when I will go ahead with the task of re-engineering the application to manually insert the MPI calls for doing the various tasks like orchestration of exchange of messages or distribution of data, etc., etc. Whatever I want to achieve in parallel, I would start modifying my code using the base language and the MPI routines to accomplish that. And once I'm done with this re-engineering activity, I might end up with a parallel application, which you have to test and, of course, run. And you might see that while running the program, there is a lot of opportunity for optimization. So you might want to go back to the application, re-engineer it again, and optimize it manually or by using compiler-based optimization strategies. So that's the typical workflow that I follow for parallelizing my applications with MPI. So I'm not saying this is the standard, but this is very often seen that you would want to have a working sequential application first. Okay. And to give you a general overview of an MPI program, there's this diagram, and this is from a very interesting tutorial. If you follow the link on the slide, you will go to the tutorial from the Lawrence Livermore National Lab for MPI, and this is an adapted version of the diagram from that tutorial. So you will see that in a typical MPI program, you will have multiple processes. In the diagram here, I'm showing two processes executing the copies of your program. Okay, and each copy of the program will be similar. You're just running it on different processes, and each process knows what it needs to do for its part to contribute to the global computation. So typically, you will have an MPI include file at the top of your program. I'm assuming that we are writing a program called myprogram.c. So you will want to include a header file, mpi.h. And then you would want to extend your declarations, and you want to probably, the first thing you want to do is initialize the MPI environment. Then you want to do some work in parallel. And after you're done with doing your work or computation in parallel, you want to terminate the MPI environment. Okay, and that's that region that you see in the red box. That's the one that's related to the parallel execution. Okay, before that and after that, the programs can work serially. So that's about like giving you a high-level overview of how things work in a distributed memory programming paradigm and how a typical MPI program looks like. And now let me tell you about a few basic terminologies that I will be referencing when I explain you the different MPI routines that you can use for writing a parallel distributed memory program. So there's a notion of communicators and groups that you want to be familiar with. So communicators and groups are objects that are used to define which collection of processes may communicate with each other. So, for example, think about a group of chefs who excel at making Asian cuisine. Then think about a group of chefs who excel at making Italian cuisine. So these are two different groups. So if you have a person named John in each of the two groups, there's a chef named John. So how would you know which John you're talking to? You want to have an identification number, right? So in order to get you this identification number, there is this notion of groups and, of course, the ranks within the groups. So the ranks are the identification numbers or IDs that are associated with the processes that are participating in the communication. And all the processes that are working on the communication that you specify, they represent the group, basically. So by default, MPI provides you a communicator to communicate amongst all the different processes in your group, and that's called MPI Commvault. And that's the default communicator that I will be referencing in the examples that I show you. You can define your own communicators, but due to time constraints and because it's an introductory level course, I'm not going into the details of how to define your own communicator or how to define your own subgroups from a bigger group of processes. So we are assuming here that all the processes that you have requested to run your job with, you're going to do your computations with probably all of them. You're going to use them as a default group, but not like creating subgroups there. And but just be aware that you can create multiple subgroups out of the default group, and you can create multiple communicators. Okay, but we are going to work with just one communicator, which is the default communicator called MPI Commvault in this session. So if you go back to this diagram that I showed you, I told you that we need to have some functions or routines to initialize the MPI environments. And now I'm going to tell you about these initialization routines which come under the category of MPI environment management. So the first routine that I want to tell you about is MPI init. So if you are C programmer, you would know that, like you would recognize that the left-hand side of the table is C, and Fortran programmers, you would recognize that the right-hand side is about Fortran syntax for the same thing. So you would notice that if you're writing a MPI plus C program, then you would have to include mpi.h header file, and the syntax for that is given. You have to do it like this. And if you're on a Fortran program, I'm also showing you how to include the Fortran header file, include mpi.f.h in single quotes. And then if you have to be aware about the syntax of specifying the MPI routines. So in C, the MPI routines begin with MPI all in caps and underscore, and oftentimes each routine will have its first character, like after underscore in caps, and rest of the stuff is in lowercase. So that's the syntax that you want to be aware with. For Fortran programmers, you can have all caps or all lowercase syntax. And in majority of the MPI routines, the only difference between C and Fortran is the last argument. So in Fortran, majority of the routines would have, MPI routines would need an extra argument in the end. It's called it's the error argument for capturing the error code. It's IERR, probably here in the slides. You can call it anything, but it's basically an integer value that we define and we pass there. But C programmers, when you call this function, it would return a code that you can then access and store it in any variable and use it for your housekeeping purposes in the program. So that was about the general syntax in the header file. Now let's look at how do we initialize the MPI environment. Remember that every MPI program, when I say every, it means every MPI program ought to have a header file called mpi.h, and they ought to have an MPI initialization routine called mpi_init. Okay? Without this, whatever you write is going to be reported as error by the compiler. Okay? So you have like MPI init for initializing that MPI environment, and then once you're done with your stuff, you have to gracefully exit from the MPI environment, and the routine for that is MPI finalize. So when you call the MPI routine in your program, that will terminate the MPI environment that you initialized with MPI init. So one thing that C programmers would want to know about is that the MPI init routines, you can pass null to it. So beginning MPI standard 2, the MPI init can take the null values. Okay, prior to it, you had to have argc-argv, but now you can pass null values. Okay, and the other version is when you pass argc and argv arguments. If you are a C programmer, I'm assuming that you're familiar about the signature of the main function that accepts argc and argv, right? Why do we need that? For passing command line arguments, right? So so if you have a function wherein you're accepting argc and argv values, and you want to pass that to the MPI environment, you can use argc-argv like this. But the latest implementations, they can also work by passing null. They can pick the environment. So you have to test the implementation, which implementation can accept null, which doesn't. Okay. So, and the MPI finalized routine is what I told you, is used to terminate the MPI execution environment. So that's just the basic syntax. And I told you about, till now, communicators, groups. I told you about rank, right? Now I'll tell you about a few more terminologies before I move to show you the real example. But let me also summarize about the routines that I told you so far. I told you about MPI init, which is used to initialize the MPI execution environment, and MPI terminate, that you would, MPI finalize, sorry, that you would use to terminate the MPI execution environment, right? And I told you about the fact that every MPI program ought to have a header file, and that is mpi.h. Okay. Now let me tell you about a few more terminologies or concepts. So, and these are related to the arguments to MPI routines. So I will be showing you some MPI routines, okay? So when I say buffer, I would mean the name of a variable, including arrays and structures, that is to be sent or received across the processes, okay? And this is basically an argument that's passed by reference. That's what C programmer might want to know. And it usually must be prepended with ampersand. So if you have a variable named x that you want to pass from one process to another, so your buffer would be ampersand x, okay? So that's about buffer. You could pass, like I said, arrays, structures, variables, but we would refer to everything as buffer here. And then you want to know about the data count. Data count is the number of data elements to be sent or received amongst different MPI processes. Data type would be could be elementary data type or derived data type. Now, C programmers, what are the elementary data types? You already know about, right? Int, string, no, not in C. Char, char, float. How about double? Double, right? So likewise, there's no Boolean, right?
No.
And there's no complex, right? But Fortran guys have those Boolean and complex types too. So all these types which are defined by the base language, they are the primitive data types. So you could be passing those in your MPI routines, or you could have derived data types. Now you could have a vector constructed using MPI calls, and that could be your derived data type, right? I'm not going to delve into the details of developing or maybe describing an MPI derived type, but this is just for your general information. If it intrigues you, you might want to go back and Google it up. But this is just for general information, that when I say data type, it could be a primitive data type or a derived data type. And destination would be the process where a message is supposed to be delivered, okay? Just like when you send a letter, on the envelope you write to, whom am I sending this to, right? And I write the name of the person and the address. Likewise, you would need to specify the destination of your messages that you're sending across the MPI world, right? And that's the group of all the processes that are there in the that are part of your computation. And then the source is, of course, the process that's initiating or originating the message, okay? So just like on your envelope, you would write from your name, that likewise in the message, you have to write, okay, this is the source. And there would be an argument for specifying the source process, ID, okay? And then there is a notion of tag. Now, tags are non-negative integer values to uniquely identify a message. Now, imagine there are messages going all around the processes, and each process needs to pick the message that's meant for it and needs to process it and do the communication. So, in order to make the processes understand which message is meant for them, you can specify a particular tag on which they can take action. Okay, you can write your program in such a way. However, well, if you don't care about any tag, you say, well, I don't care, just process every message you get. You can use the any tag. There's a pre-described tag you could use. I'll tell you more about that later. So that's about tag, and then there's status object that you want to be aware of. So in MPI world, you basically work with message passing, like I told you. So message passing, of course, is like there has to be somebody sending the message, there has to be somebody receiving the message. So if the sender or if the receiver, well, if the sender wants to send a message, they want to invoke an MPI call for sending. If the receiver wants to be receiving the message, they want to have an MPI receive routine, for example. Okay, I'll tell you more about these routines later. But just to tell you about status. Status is passed as an argument for a receive operation, and it indicates the source and tag of a message. Where is it coming from? That a process can find by looking at the status object. And request is a unique request number that is issued by the system, and it can be used to check if a particular category of operation has completed or not. And I will explain you more about request object when I tell you about asynchronous, immediate mode of communication. So coming back to the topic of environment management routines. So far we have already seen two routines, MPI init and finalize, right? There are a few more like those that help you manage the environment of MPI for MPI programming. And one basic routine is MPI comp size. Okay. This helps you determine the number of processes in a communicator. Okay. So the example I was giving you regarding for loop. So I told you that if you have a for loop that computes the sum of first 100 numbers, and you want to do it like, okay, if I have two processes, I want to say process 1, you start the computation from 1 to 50, and process 2, you start the computation from or maybe you find the sum of integers 51 to 100, and then you would combine the sum, right? Now, what if you have 4 processes? You want to engage 4 processes in doing your computation. Then each will get how much of work? 1 to 25, 25 to 50, 50, then so forth, right? Each will get 25 elements to work on. Okay. In order to compute the amount of work that you want to send to a process, this is a handy routine. You can call this routine in your program, and you can find out how many MPI processes there are that are participating in your communication or computation. And then you can say, okay, I want to evenly distribute the task, or I want to have a particular, some other distribution of doing some kind of distribution to spread across the work across multiple processes, okay? So for doing that kind of work, this routine, MPI comp size, comes handy. As I said, it determines the number of processes in a communicator. And if you look at the syntax, the C syntax looks something like MPI comp size, where C of com is in caps, just everything after C is in small, like lowercase. And then it takes 2 arguments. The first argument is com, or the communicator. The second argument is ampersand size. Okay. Now, C programmers, I told you about passing buffers, and I told you that whenever you want to pass even a variable, it's passed by a reference, and you have to use ampersand. It's the same thing. So size would be something that you define in your program. Let's say an integer value, int size, and when you pass it to this routine, you say ampersand size. Okay. And I told you about a default communicator. I told you that MPI COM is the predefined communicator that you can use to communicate with processes in your group. So wherever you see the argument com in this API, in this routine, like com size, the first argument, you can replace that with MPI com world. Okay. So that's about C notation. Fortran programmers, you would notice that in addition to com and size, there will be a third argument called iError. Okay, and it's again an integer value, and the explanation of com and size is the same like I just gave for the C programmers. So just to rehash, MPI com world is the default communicator that MPI provides you. Okay. And if you have MPI com world specified in this function call, you have, let's say, MPI com size, bracket open, MPI com world, comma, ampersand size. If you have just that, then that would imply that size is set to the number of processes that are participating in your computation. It takes care of, it accounts for all the processes. If you launch your program to run with 10 processes, your size would be 10. If you launch a program with 100 processes, the size would be 100. So you don't have to hard code the values you see. You can dynamically get that value by calling this routine MPI com size, right? So that was about MPI com size, and then there is com rank. So MPI com rank determines the number of processes within a communicator. Okay, so if you have 10 processes, the counting of each process would begin by 0. The counting of the processes would begin with 0. So first process would be rank 0. Second process would be rank 1, and so forth till you reach nth process, and its rank is n minus 1. Okay, so it determines it basically is used to assign the identification number or ID to each process that's participating in your communication. So as I said, MPI com rank gives you the identification number. So it's a number, okay? So therefore, this argument rank, the second one that you see in this function call, that's an integer value. So you have to define something like int rank in your program, and you have to pass rank by reference in this function call, okay? And Fortran programmers, you might want to know that, just like MPI com size function call, you'll have an extra argument here, and that's iError, okay? So that's about, by this time, we have seen 4 routines already, okay? Before I get to the example to show that, how to use that, let's quickly recapitulate. So we had MPI init to initialize the MPI environment. We saw MPI finalize to terminate the MPI environment. We saw MPI com size to get the number of processes that are participating in the communication or computation. And then there is com rank, which you would use to assign a specific ID to the which you use to get the specific ID assigned to each process working on the computation, right? So think about it. How can you use it? For example, if you want to say, let's go back. I'll keep going back to the same example of counting the sum of first 100 numbers. Now let's say I'm process 0, Jason is process 1, a friend here in the first row is process 2, and a friend here in the third row is process 4, right? So we have 4 processes here. Our numbering would be 0, 1, 2, 3. I want to say if rank is 0, then do the sum of first 25 numbers, which is 1 to 25. If rank is 1, which is Jason, he would compute the sum of next 25 numbers, which is 26 to 50, and so forth. So you're assigning tasks to each process. That's where a thing like rank comes handy. And so does size. Size helps you communicate the chunk. Like this much of task goes to each process. Rank tells like exactly what size or what data goes to what process for computation, right? So I hope this is clear. If not, feel free to ask questions. And the next routine that I'm going to tell you about is WTime. It's a wall clock timer routine that you could use to time your, to gather the time spent in a particular section of your program. So let's say you want to measure how much time was spent doing the computations in a for loop. you might want to call MPI WTime at the beginning of the for loop and then at the end of the for loop, right? So this MPI WTime returns the elapsed wall clock time, and it would return a double value. So you might want to have, let's say, a variable called double T1 defined. So you would say T1 equal to MPI WTime before the for loop. Likewise, you can have a variable T2 defined, and you can say T2 is equal to MPI WTime after the for loop. Then if you take the difference between T2 and T1, you will get the time spent in the loop. Is that right? Okay. So you would notice that here, Fortran guys do not have to pass any extra argument like error or anything like that, right? So the the number of arguments the C binding for this call takes and the number of arguments that the Fortran version takes is the same, which is 0. Both do not take any arguments, right? So as I was telling you, that majority of the MPI routines accept an additional argument, error at the end of the argument list, and that's the difference between the C and the Fortran versions of the routines, right? So, and I told you about an exception already, which is WTime. WTime does not take error argument, and so is WTIck, which is another MPI routine, which I will not tell you anything about. So coming back to this error thing, as I told you, for Fortran programmers, I'm just wanting to repeat this. error is an integer and has the same meaning as the return value of the routine in C. Okay? And in Fortran, MPI routines are basically subroutines and are invoked with a call statement. If you flip to slide number 67, you will see examples of how to use these routines. And note that all MPI objects are of type integer in Fortran. Okay? So now let's look at our let's move towards our first MPI program, okay? As I was telling you about the typical workflow that I follow, and again, that might not be the standard procedure, but that's what I follow, and that's what I'm going to tell you about. So I was telling you that I start with a working serial program, right? And here is an example of a very tiny working serial program. All this program does is print a string, wonderful class in the string, okay? C programmers recognize this already, and Fortran programmers, if you don't recognize this, don't worry, go to slide 67 again, I repeat that, and if you can follow the C syntax, it's wonderful. So you notice that from the slide that if I have to compile this program, all I have to do is ICC, that's it, if I'm compiling with Intel, or I could use GCC if I'm compiling with GCC compiler, okay? So I invoke that command to compile this program, and I specify the output name. I say -o example1, my name of executable, and I compile the program, and the name of the program is example1.c. Okay? So I hope this command to compile the program is clear to all. And once I've compiled the program, I can run it by saying /example1. Now that prints the message wonderful class on the screen. Okay. I hope I do not have to explain this program. Does everybody understand this program? Okay, very good. So that's how all this does is prints the string wonderful class on the screen. If I have to convert this to an MPI program, the first thing I want to do is, as I said, include the header file. And for C programmers, the header file for MPI that you want to include is mpi.h. And I think for Fortran, I said it's mpif.h. And that's what you have to include in your program. And that's the first thing. Next thing, I told you that every MPI program ought to have an MPI initialization environment. That's why I have MPI init here. Note that I really don't care about passing anything to the MPI environment. It's just a plain function, main function that just prints a string to the screen. I can just live with passing null arguments to MPI init. Okay. And what's the next basic thing I told you about that you ought to have in every MPI program, besides including the header file and besides having a startup routine? Rank and size you can live without, even if you don't have rank and size. Your program will finalize. Perfect. Thank you. And and you have to remember to shut down the environment, right? So you ought to have MPI finalized. So this is the very basic version of an MPI program that you can run on n number of processes, and all the processes will print the same message, wonderful class, on the screen. Now this is pretty much the most useless program that one can write, right? What's the whole point of writing a string in parallel on X number of processes? But the whole point here is to demonstrate the syntax and semantics, as in how would you include a file, how would you call a function, like an MPI routine, etc., etc. Now that we have this very basic MPI program, let me tell you about how to compile it and run it. Well, I just mentioned about passing null to MPI init, and I've already explained to you about that, so I'm skipping slide number 21. And let's go straight away to compiling and running MPI programs. So note that on Stampede, the default MPI implementation that's available is MVAPage2. We also have Intel MPI that's available, and you can switch to that by invoking the module swap command. And more information about that is in the user guide as to how to use the module swap command. So the Intel MPI is known as IMPI, and the MVAPage2 is MVAPage2. So if you have to swap between the different implementations, all you do is module swap MVAPage2 and IMPI. Basically, that like brings the Intel MPI stack to your environment, basically. But as I said, the default MPI implementation on Stampede is MVAPage2. Okay, and by default, you have the Intel compiler available on Stampede, and there's also a GCC compiler module that's available that you could use. And also note that only 64-bit versions of the MPI libraries have been built on Stampede. Okay, so if you are bringing in a program from some other machine, let's say if it's very ancient, you anyways have to, the rule of thumb is if you bring a program to Stampede, just recompile it. But if you had an executable from an older 32-bit machine and you're trying to run it on a 64-bit machine, that might not work, and you have to remember to recompile your program when you port it, right? Okay, so, and also you want to be aware that the libraries that you might need for your software, let's say MPI is what we provide, but in addition to MPI, if you need some other libraries, those you might want to have the 64-bit compatible libraries, right? Okay, so if you have to compile the program, the MPI program I just showed you, that's the command you would use. You would say MPI-CC. Earlier I had ICC. Now I'm having MPI-CC, okay? And rest of the stuff is pretty self-explanatory. Just like in ICC, I specified the name of the executable with the -O flag. I'm doing the same thing here in this command. I'm saying MPI-CC -O MPI example1, and the name of the program is MPI example1.c. Okay, that's a program I'm compiling. And note that on Stampede, if you have a C program, C plus MPI program to compile, you can use MPI-CC. You can also use MPI-CXX, right? So it's not that you can't have C++ programs with MPI, but just that, as you know, C is somewhat a subset of C++, not in true mathematical sense, not right, but it's somewhat like everything that you can do with C, probably you can end up doing with C++ too. The syntax is supported. So you could use the MPI binding for C from within your C++ program, right? That would work without any problem. But when you're compiling that program, you have to use MPI-CXX, not MPI-CC, okay? And if you are a Fortran programmer, you want to be aware that you want to use MPI-F90 to compile your MPI program written with Fortran. Okay. Now, let's look at how to run this example program that I just told you about how to compile. So if you go to the Stampede user guide, so if you're working on Stampede, I recommend the first thing that you do is familiarize yourself with the Stampede user guide. go through the sections on running applications on Stampede, and therein you will learn about how to write a job script if you have to work in the job or the batch mode, or how to run the program interactively on a compute node. And also remember that we highly discourage people running programs on the login nodes, okay? So this is just the trivia. So go to the Stampede user guide and you can get hold of the script named myjob.sh. We have provided the script as part of the tarball that you will use for your hands-on session, so don't worry about it. This is just for your general information. So once you have your job script, let's call it myjob.sh, you can submit the job by using the sbatch command. You can say sbatch and the name of the job script, myjob.sh. And within this job script, I will show you what it looks like. You will have a command to run your MPI program. Okay? I will show you this job script in a bit. So that's about submitting the job in the batch mode. Now, if you need to get hold of a compute node to work interactively, that is, you need interactive access and not the batch access, you can use the srun or the idef command. Both srun and idef commands are explained in the user guide, and we will not be using that in today's session, like in the lecture part, but during the lab, you're free to try those too. So, and remember that Stampede has 16 cores per node, okay? So if you have to run your program even with, let's say, 2 processes, or maybe 3 processes, any amount between, let's say, 1 to 16, okay? For that purpose, you're requesting access to 1 complete node, okay? This is just for general information, for your accounting purposes. You will be built on the node basis. Irrespective of how many cores you use on a node, we bill you, the service units we use to charge people is on the node basis. So you will be charged for all 16 cores, even though you use just 1 core on a node, because that node is dedicated for your computation purposes while you requested access to that, okay? And also remember that when I use the words MPI processes or tasks, they are the same thing. I might use them interchangeably at places. Okay, after all that trivia, let me show you an example job script. So in here, you will see some directives for writing commands for the job submission system, if you will. You can imagine it as if you're telling the job submission system that your job name is myMPI. That's the first line here, second line here. Pound sbatch -j myMPI, right? You specify the job name, you can call it anything. Then you specify the name of the output file. Now, we saw one type of output file already. That was the executable that you got by compiling your program, right? Now, when you're running the program in a batch mode, after your program has finished execution, there could be error files or output files produced. There could be 1 or 2, depending upon what you specify in the script. So I recommend go back to the user guide and read the syntax of that. So when I say -o here, all I'm saying is all the errors produced or all the standard output produced while my job was running, please send that to this file named mympi.o%j, where j is the job ID. So every time you submit a job, if you have %j there, this mpi.o will get appended, this whole thing will get appended with the job ID, the one that you get after submitting the job, okay? So, and here I'm saying sbatch -n32. So when I say -n32, and I told you that each node has 16 cores, all you're doing here is requesting 2 nodes, right? One node has 16 cores. When you say -n32, where n is in lowercase, that means you're requesting 32 cores on 2 nodes, okay? There's also a -N, which I will be skipping the explanation all, but there you explicitly say how many nodes you want. For example, though you have like 32 cores that you want to run your job with, but let's say the memory needs of your jobs are such that you cannot fit 16 MPI processes on 1 node, or maybe 32 processes on 2 nodes. And let's say you want to spread it across 4 nodes, or maybe 8 nodes, or maybe even 16 or 32 nodes. Then you can use minus capital N to specify the number of nodes you want to use to spread across 32 MPI tasks across, okay? And then you have to specify the queue name. So with minus P flag or minus P option. So when we say minus S batch minus P normal, all I'm saying is run this job in the normal queue. So there are a bunch of other queues that we support on Stampede. And for this again, to select which queue is best for you, please go through the user guide. So one queue which you might find handy for your quick development and testing work is the development queue. It gets you access quickly, but for a very short duration of time and on very few number of cores. Okay, so that's the queue you can use. And then you have to specify the anticipated time that your job might take to run. So here I have S batch minus T. I'm specifying 1 hour and 30 minutes. I'm saying my job will take 1 hour and 30 minutes to run. I could be lying here, or it could be an overestimate, a very gross one. Though my job might take just few seconds to run, I could be saying 2 hours here, right? So it has both pros and cons to do that. If you underestimate, if your job takes 10 minutes to run, but you specify 5 minutes, then your job will exit the queue without completion because you just specified 5 minutes there. But if you overestimate, the downside is your queue waits time might increase. So what you might want to do is have a very close approximation, the best possible approximation you can make for running your jobs here. You can say, well, it's not like, for example, that's the first time you're running your job. You can put an approximate number and see. By hit and trial, you will figure out what's the best timing for your particular job to run on Stampede on the specified number of cores. Okay. So that was about time, and then you have to specify the account to which you want to bill your SUs. Okay, and that's specified with -A. So for the purposes of this training, we have assigned the training accounts to you, and hopefully you have you're added to that allocation, and you will be able to access that account here. So people who signed in from the TAC user portal have their own name for the project to use, and people who registered through Exceed user portal have a separate project name to use. And we have those listed on the slides for the labs. So give me just one.
They'll be on the allocation for about 2 weeks.
Yeah, you'll be on the allocation for about 2 weeks. Even if you're unable to finish the lab session today, just not worry about it, because everything that I want to tell you is there on the slides, and the exercises are there in the form of the tarball, and you can use the access that we have provided you for the next 2 weeks to try the exercises at your own leisure. Okay, so that was about SBatch, everything that you need to specify, right from the job name to the output file name to the number of cores, the queue to use, the time, the anticipated time, and the account number to build the job to. Okay. So set -X. So I tend to be a paranoid when I'm running jobs. I want to see what if I have multiple commands in my script. I want to know which command produced what result. So what I'll do is I'll put this set -X. What it does is it echoes the command first to the output file and then puts the result there. So if you say, let's say, cd a particular directory, it will tell you that cd plus cd directory path. So you know, okay, you switched to a directory before the next thing was executed. So set -X basically echoes the commands that you put in the script to the output file. Okay. So that's set -X, and then this is the cute command I was going to tell you about to run the program in parallel on Stampede. Now, IB_run is the wrapper for MPI run and MPI exec commands, and it's meant to be used on TAC resources, though there are other resources that could have their own version of IB_run, and there are other resources which might not be using IB_run. They might be using something else like MPI run or MPI exec or MPI exec Hydra or MPI run Hydra, whatever. There could be a number, depending upon the implementation and depending upon the service provider. You might want to see what MPI run command to use on that particular system. Okay. Typically, like on not typically, like on TAC resources, we have IB run. So if you have an MPI program to run, you run it through IB run command directly. Okay. There are some workarounds, you can cheat, but just use IB run at all places. So that's about how to specify the job script. And I already told you that in order to submit this job script, you would use the sbatch command, this one. So whatever I have in this file, this one, I put it in the file named myjob.sh, and I submit it to the queue by the command sbatch myjob.sh. Fine. When I run it, I get this kind of output that you see on the slide. It says cat mympi.o 2339942. Now, does this ring a bell? I told you that whenever you submit a job, you get a job ID, and as per the script, the job ID gets appended to the name of the output file. So here I said my output file should be mympi.o%j, and my job number was 2339942, so %j got substituted by that, and that's what I get in the output file. Is that clear? Okay. So once the job has finished running, you will see that whatever is in red color, wonderful class, that came from the program that we wrote. Rest of the text came from the job environment, if you will. That's something that you did not do, but it will be there every time you submit an MPI program. You get an output file. You will notice that we have some lines inserted in the job in the output file, like starting up job, setting up MPI environment, etc., etc. Then shutting down MPI parallel environment, etc., etc. So if your program crashed or produces some erroneous output, this is the place where you can go and see what was it that went wrong. Okay, and that's one useful feature of this thing, right? Now, after looking at that very silly example of printing the message wonderful class on the screen, let's look at slightly better example. Like our friend said here, we could use com rank and com size, right? This example shows you just that. So as in the previous example, we have include file at line number 2, we have include mpi.h, right? And then we extend the variable declaration section here, and I say declare 2 variables, rank and size of type integer. Okay. Then I'm invoking the MPI routine MPI init and passing ampersand argc and ampersand argv to it. Now, because my main had argc argv, I just passed those here, argc and argv to MPI init. Okay. Now, the whole purpose of this program is to demonstrate how to use rank and size. It does nothing special beyond printing one more message to the screen like the previous one, but here you would see that we are printing rank. Now, my example, I intended to include like size also in the example, but I just did not want to extend the PowerPoint content too much to the extreme. That's why I just put rank there. But using this example, you can also print the size of your MPI, of the number of processes that are participating in the communication, okay? So at line number 6, you see the syntax for MPI com rank. So we are finding the rank associated with each process participating in the communication. And you notice that the first argument is the communicator, which is the default one, right? MPI com world. That's the one I told you about earlier. MPI com world, all in caps. And then I'm showing you how to use MPI com size in the program at line number 7. And this again takes 2 arguments. First is MPI com world. Second is ampersand size. That is, I'm passing the variable size by reference. Okay, that's a buffer. Then at line number 8, I show you how to print the message MPI hello MPI world from process. Okay, %d and rank. All this does is, each process, when it prints this message to the screen, it also prints its rank or the ID associated with itself. So if I'm printing this message, I will append the message with my rank, hello MPI com world from process 0, then from process 1, and so forth. That's the whole purpose of this program. Okay. And then I have MPI finalize. Okay, I show you how to use the rank, and I call finalize and shut down the program. When I run that program, I might get an output like this. I say I might because there is no particular order to which the messages will get printed to the output file. If process 1 arrives before process 0, the first message will be printed by process 1, next by process 0, and so forth. So it's non-deterministic as to which process will print the message first. There are ways to control that, which we are not looking into now, but that's about what you would see from the program that we just saw, right? You see in the end of every message printed in red, there's a number, and that number corresponds to the variable rank that we saw in the program. So far so good. Any questions? Okay. Now, having told you about the very basics of environment management routines, how to compile a program and how to run a program, let me tell you more about MPI routines. I'm going to tell you about point-to-point communication routines and collective routines. Okay. When there are two processes engaged in a communication, you call that point-to-point communication, right? So if I just go and whisper to a friend here on the first row in her ears, that's like what I'm saying is just meant for her, only she's hearing that. And whatever she says, if she whispers into my ears, she's just saying that message is for me, right? It's just we two people talking. But when I'm talking to the whole class, like I'm doing now, in the broadcast mode, that's called a collective mode of communication, right? So first we'll look into point-to-point communication, wherein there are two processes engaged in the communication process, in sending, receiving, and doing other things. And then I'll tell you about the collective communication later. And please be mindful that the send and receive routines that I will tell you now for the purpose of communication between two processes only. So remember that for every send routine, you have to have a matching receive routine. If you do not have that, your program will deadlock, and you will pretty much not get to any point in your computation. So in order to avoid the deadlock situation, you have to pair up. You have to have a matching receive for a particular send. Okay? So I just wanted to have a pretty picture to explain what I just told you about the point-to-point communication. So in this diagram, all I'm showing is there are two processes engaged in this point-to-point communication. One takes the role of a sender, and the other process takes the role of a receiver. And what we are doing is we're trying to send the data from the address space of one process to the address space of other process. Just like each one of us has got distributed memory too, right? Whatever I'm thinking, unless I communicate it across to you, you wouldn't know what I'm thinking, right? I have to be vocal about it. Likewise, in the message passing world, each process that does the computation, and if that computation needs to be used meaningfully, it needs to be sent to some other process, or it needs to be processed in some particular way, right? So for that purpose, you want to do the communication. And here in this example, a process on one core is sending the process on another to another core, and these cores could be on the same node or on different nodes. Okay. So there are the point-to-point communication routines. There are two broad categories: set of send routines and set of receive routines. Okay. Now the send routines, they could be of certain kinds, and the receive routines could be of certain kinds. So there are blocking send and receive routines. There are non-blocking send and receive routines. And there are combined send and receive routines. Then there are three routines for which there are no corresponding receives per se. You could use any one of the blocking, non-blocking, or combined modes. But there are some special modes of buffered send for the sending processes, which is called like buffered send or ready send or synchronous send, and we're not going to see any bit of that in today's lecture. I'll tell you more about blocking, non-blocking, and combined routines for point-to-point communication. So blocking when I say routine is blocking, what I mean is the routine only returns after, if it's a receive routine, for example. There could be a blocking send and there could be a blocking receive. So if it's a blocking receive routine, it will only return after the data has arrived and it's being used. Okay. Till the time the data has not arrived, the process will block. It will not proceed to do something else. Okay. And a blocking send routine returns after it is safe to modify the application buffer to reuse. There's a notion of an application buffer and a system buffer. So application buffer is everything that you have access to through your program, like when you have a variable defined or an array defined. All those things come under the category of application buffers. System buffer is something that's implementation dependent. And I don't think we'll have time to delve very deeply into that. But how it works, I might give you like a brief explanation of that in upcoming slide. But just know for general knowledge purposes that whatever you do in your program comes under the category of application buffer. Okay. So I was telling you about blocking mode of communication, blocking sends and receives. And analogous, like we have blocking send and receive, we have non-blocking sends and receives. Now, the reason why we call these routines as non-blocking is when they do, when they have done their job, they return immediately. They don't have to wait for other process to participate or do something until they really want to check on something for accuracy purposes. Okay, it might sound a bit confusing, but let's take an example. If I'm sending a mail via regular surface mail by USPS, I just put the address of the receiver and I put it in the mailbox. I can't do much about it. The mail will reach to the recipient, and then I can call them. I can say, hey, did you receive my envelope? They can confirm, and then that's when you will know, right? But if I'm doing like a person-to-person delivery, as in I'm the person who's delivering a message, and I want to go and say, hey, here's your food packet, give me the money in return. It's all happening such that till you give me the money, I'm not giving you the food packet, and I'm not going to leave, right? So that is like blocking mode. I do not proceed to leave till I receive money from you until I have delivered the food packet to you, right? But look at the opposite scenario, wherein you have to go back to check later. But once you have to send the message, you send it and you move on to do the other things in your life, right? That's the purpose of non-blocking communication. And it's often used for overlapping the communication with the computation, and it's an optimization strategy. And I encourage you to look more into that at your time. And I also want to forewarn you that it is unsafe to modify the application buffer in your program until you know for sure that the requested non-blocking operation was actually performed. So though you have let's say a buffer named X, you want to copy its contents to the address space of other process, okay? You should not change the values of that buffer if you have to use that later in your program meaningfully, unless you have polled the other process and checked with them if they received the message you sent them, okay? That's something that you as a programmer have to make sure if you're using non-blocking routines. Okay, now coming back to the very less interesting part, which is the syntax, okay? So let me show you how to specify the MPI send routine. So it takes basically 5 arguments. The first argument is the buffer. Oh, 6 arguments, sorry. The first argument is the buffer, which is the initial address of the send buffer. The second argument is the count. You have to specify how many items are you wanting to send to the other process. Then you specify the data type. Then you specify the destination rank. Whom is this message meant for? Then you specify any tags or message IDs if you want. And then you specify the communicator. Now, as I told you, you could use the default communicator, which is MPI convert. Wherever you see the conf, MPI_com, you see that as the last argument. In place of that, you could use MPI COM-word. Okay, and some elementary data types in MPI that you want to use for, let's say for integer, you could use MPI int, all caps. If you're sending double types, you can use MPI underscore double, all caps, and so forth. Okay. Now, coming to the receive part. This guy has one argument more than the previous routine, and that's the last argument that you see, which is status. Okay? The first set of arguments are the buffer address, which buffer should be used for receiving purposes, then the number of items to receive, the type of the data that we are receiving, and the source. Who is the sender? We want to know that. Okay? And we want to have a tag or a message ID. We want to have a communicator. Okay? We want to know if there are multiple subgroups, whom am I receiving the message from? If I'm using the default communicator or the default group that we get, what will I use there? MPI COM-word. Instead of MPI COM, we will use MPI COM-word, right? If I want to use the default communicator. And then the last argument is MPI status. So the status object returns the information on the message received. It indicates the source of message and the tag of the message. Okay. Now that's the syntax of the receive message. I'm not sure if we would do much with send and receive routines in the exercises. I basically have written the exercises to show you the usage of the collective routines, and there's a reason for that. That if you are very curious, I can tell you individually. And for now, know that if you know how to use MPI environment management routines, the 4 ones that I told you, init, finalize, comrank, comsize, and these 2 routines I told you, sends and receives. Using these basic 6 routines, you can pretty much write any MPI program that you want to write. Of course, you can use MPI WTime also. Those are the most basic routines. But of course, you need some flexibility. You don't want to deal with all the low-level details, right? And that's where collective routines come handy. They have some patterns of communication that each implementer has their own way to implement a particular pattern of communication, like broadcast or gather, etc. So you could use that instead of like doing all the hard work using sends and receives. Okay. So, but just suffice to say that if you know how to use these 6 routines that I just mentioned, feel confident that you can write any MPI program.
To send and receive, it's possible 2 sends, 1 receive.
2 sends. For each send, you have to have each receive.
Okay.
So 2 sends means 2 receive.
Oh, okay.
So here, let's look at an example of a blocking send and receive in the code. So this is not the complete code, just a small snippet of the code. I'm just trying to show you how to use the send and receive routines in the code snippet. So I meant to say that if my rank is 0, then set the values of destination as source as 1. So here all I'm doing is I'm thinking, or my program is centered around 2 processes, process 0 and process 1. And I'm saying, if I'm process 0, I want to get messages from process 1 only. Though if there are 2 processes, it might look silly, but that's what we are doing here. Like, if rank 0, receive from process 1. If rank 1, then receive from process 0. Basically, that's what this if-else does, right? Okay, let's look at the body of if-else statement. We have destination and source set to 1 for rank equal to 0, the if part, okay? And then we say MPI sends, we specify the arguments for MPI send. We say out message, that's the send buffer address. Then we specify 1. We say how many elements are we sending? The count. We're sending just 1 element, okay? And the type is character. That's why we say MPI underscore char. And we specify the rank of the destination. What would be dest here? 1, perfect, because we defined that to be 1. And the tag, I could have like set tag to MPI tag any, MPI any tag, Okay, that's not shown in the snippet here, but I specify the tag there. Then I have MPI COM world, which is the default communicator. That's how I write my MPI send routine. Now, I told you a few minutes ago that every send has to have a receive, otherwise your program will deadlock. So for this send that I just showed you, this statement here in the if part, I have to have a corresponding receive, and that's written in the else part here. Okay, so let's switch from this line here, MPI send in the if part, to the MPI receive in the else if part. So here I specify the address of the receive buffer, and I say that my dest and source are 0, right? So in the routine I say that the receive buffer is in message, the number of elements I'm receiving is 1, the type is MPI character, the source, the tag, then I specify the communicator, which is MPI COM world, and I have one more argument, the stat argument. So if you have to define stat, you have to say like MPI underscore status. That's the type that you have to use to define stat. You will see examples later in your hands-on exercise. So that's how you define the MPI receive. And again, for every send, you have to have a matching receive. Okay. And now if you look at the if part, there is a receive, which corresponds to the send part in the else if part. Is it making sense? Okay, wonderful. Okay. Now this, yeah. No.
Shouldn't be a first send and first send and first the receive in a second. Else it be the same tag.
So if I say MPI any tag, what I'm saying is like, I don't care whom this message comes from. Because you have the source here. I know whom this message is coming from with this. But if my source is sending multiple messages, I say, if tag is blah, 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 do X. If tag is blah, 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 then do Y. So if there are just one sender and receiver participating, and you want to distinguish what they want to do depending upon the messages sent and received, that's when the tag thing will come handy. Okay? But in this example, it's immaterial. Now let's go to this example here. Point-to-point communication, again, a snippet like I showed you before. But this code is going to deadlock. And do you know why? Yeah, they are both in the receive mode. Nobody is sending. So this receive is a blocking receive. It's not going to do anything else till it receives a message. And the same for the other process. Both will keep on waiting for a message, which no one is sending, right? That's why this code will deadlock. So you have to be mindful to avoid such scenarios in your program. And one way to avoid this, as I said, is to have a matching send and receive. Other way is to have send receive combined calls. Okay, look at this API call here, API routine, the MPI routine here. So I have MPI underscore send receive all like combined. So all the arguments that you see in this function call, you will see that there is a set of arguments in blue color, there's a set of arguments in green color, and there's an argument in red. Let's start with the argument in red. That's the communicator, the second last argument, the simplest one. And if it's the default communicator that I want to use, what will I pass here? COM word, perfect. Okay, so we specify all the receive arguments and all the send arguments. So we have to specify the send buffer, send count, send type, destination, and send tag. And we have to specify the matching receive side. The receive, we specify who's going to receive this message by specifying here source, this green source here, okay? And then we have the receive buffer, receive count, receive type, source, like whom is this message coming from, the tag, and the status. Basically, all the arguments that you saw separately in send and receive, they end up being in one place in send receive call. Okay? So you would want to use this if both pairs of processes that you're dealing with both are engaged in sending and receiving messages. So it's a short, so if you can condense the code in this slide, like here, into one line by saying MPI send receive instead of having send receive calls like this. Okay? Okay. Now, let's move on to non-blocking communication. So, I told you that the non-blocking routines can return immediately, right? They don't have to be waiting for the process to complete, just like the blocking routines. So here, notice the syntax. The non-blocking send, it has the capital I in front of send, right? So I tells you that it's immediate send. Whatever I'm sending, send immediately, come back, do other stuff, and then check back on the status later whenever it's convenient. Okay? That's what I send is for. And the corresponding receive routine is I receive. Okay? And the arguments you are already familiar with, right? You know that for the send, you have to have a send buffer, count, type, destination, tag, com, and request object there. For the receive side, you have buffer, count, type, source, tag, com, request. Okay. The MPI request objects are used by non-blocking send and receive calls to poll, to check the status of the message in other calls. And I will show you which calls they are. They are MPI wait calls, for example, that you could use, or MPI wait any, in which you can use these MPI request objects to poll and see if your communication got over correctly or not. Okay? So let me just go to this call now, MPI wait. So it's a blocking routine. So if there is a snippet in your code that you can execute without depending upon the results or the execution status of the other process you're communicating with, you can finish that block of code or the snippet of the code, okay? And then you can wait. You can say, okay, I'm done with everything that I needed to do asynchronously. But before proceeding from this point in the code, I need to really know if the other process is done with the task or not, okay? So for that purposes, we have MPI wait routine, which is a blocking routine. So when a process calls that, it blocks till it can poll the request and status object, okay? So it takes two arguments, request and status. So this routine blocks until a specified non-blocking send or receive operation has completed. And I would highly encourage you to check the semantics of MPI wait any and MPI wait all call, and also check the semantic of MPI test. And this is all if you're wanting to use the immediate or the non-blocking mode of communication. Okay? So remember, I'm just giving you an introduction, just telling you what routines exist. But in order to be really productively using that, I recommend that you go to the manual or the documentation for the MPI specification, or go to the online tutorials and examples and acquaint yourself with all these things, right? I'm just telling you what exists there. Okay, this is about the buffering part that I promised I'll tell you. I told you earlier that I'll tell you about. So imagine a situation wherein you want to send 10 messages to other processes. Okay. And there are 10 more processes like you who are wanting to communicate with one particular process. So how do we know whose process is to be handled first? First come first serve. It's a policy here most often. Okay. Though each MPI implementation, well, let me not go deeper into this buffering part. Now that I've started speaking about it, let me just tell you only the bare minimum that you need to know for now. So, if you have to send a message from your send buffer to the receive buffer of the other process, you might imagine what happens if that process is not ready to receive the message. Where will the message sit? Okay. For those scenarios, there are system buffers allocated outside the program. That's part of the MPI implementation. So your message can go and sit in the system buffer till that process is ready to read that data and use it in the program. Okay? So pretty much that's all I'm going to tell you about system buffer at this point. But note that everything, there are two boxes in this diagram, everything that you do in your program regarding variable declaration, array declaration, structure or derived type declaration, that falls under the category of application buffer. And whatever other buffer that's provided by the MPI implementation, which is beyond your control, okay, and which can vary from implementation to implementation, that's a system buffer. That's where the process goes, and that's where the data would go and sit before the receiving process is ready to grab the data and do something with it. Okay? That's the most simplified explanation at this point. Now let's look into collective communication. So if you have one sender and multiple receivers, that's when you would think about doing collective mode of communication. Okay? So if you have a result that you computed in your program and you want to update all the processes where you about your result of computation, that's when you would use the collective communication routine. So this routine could be used for one-to-many, many-to-one, and many-to-many type of communication. Okay, and all processes within the communicator group call the same collective communication function with matching arguments. You cannot have something like if rank equal to 0, then call a collective routine. No, that will give you errors. Every time you call a collective routine, it has to be visible to all the processes that are there in your group during the communication. Okay? So that's the second bullet. That's what the second bullet there means. So till the MPI 2 standard, the collective communication routines came in just one flavor, which is blocking communication routines. Since the MPI 3 standard, there are a new set of routines that were added. Now you can do non-blocking collective communication as well using MPI. Okay? Earlier, the non-blocking mode of communication was only available for point-to-point communication. But now you could use that with the collective communication as well. And you have to be mindful that the size of data that's sent must exactly match the size of data that's received. And if you do not do that, at times your application will crash, at times you'll get wrong results. Okay? So these routines can be broadly classified into 3 categories. The routines for synchronization, the routines for data movement, and the routines for computation in the collective mode. Okay? With the synchronization routines, we typically mean the barriers that you would have in your program to synchronize with all the other processes. Okay? With the data movement, I would mean routines. There are routines for scattering data, gathering data, broadcasting data. I will show you a diagram that will explain you these things very clearly, hopefully. If not clearly, I encourage you to read more about those things. And then there are collective computation calls in which, while you're gathering the data or collecting data from multiple processes, you could be doing some mathematical operations on them, like summation or multiplication, right? So we will look into examples of those. So MPI barrier, as I was telling you, is to create a barrier synchronization in a group. So each task, when it reaches the MPI barrier call, it blocks until all tasks in the group have reached the same barrier call. Okay? So, and it takes one argument, which is MPI convol. Now, this diagram shows you the 3 or 4 types of collective communications that I just mentioned previously. The broadcast, you see that in this diagram on top, we have process 0, which has A, which has character A to send to all the other processes. Okay? It's one-to-many kind of transmission here. And that's called broadcast. So once the broadcast is done, each process will have this result A with it. Okay? Then there is scatter gather. So now with scatter, what you do is, let's say if you have a buffer of 10 elements, and you want to say that element 1, go to process 1. Element 2, go to process 2, and so forth. If you have to set up a communication like that, you can use scatter, okay? And gather is just the opposite. When you're collecting like data from other processes, they're arriving at your location, let's say, you could say, oh, element 0 of my buffer is filled by data from process 0. Element 1 of my buffer is to be filled by data from process 1, and so forth. That's when you would use gather. And then there is all gather. In all gather, it's like a many-to-many communication going on. It's like one process, each process sends its bit of data to all other processes. So what they end up doing is everybody is talking. Like if while I'm talking, you start telling me something. So it's going, like, to us it's going to sound like a huge commotion being created. But in MPI world, they have like things like tags and source ID, destination ID to make sense out of everything, right? Yeah, you have a question?
For scatter, what you show for evenly distributed data to each process is possible if you have 5 A, B, C, D, E.
Yes.
E go.
Okay. So if you have, let's say, A, B, C, D, you want to have that amount of buffer allocated on the other process too. So they have to have that amount of buffer, otherwise your call will fail. So you remember I told you that the count of the data being sent and being received have to match. So if you have a buffer which is like 10 elements long, and you're wanting to send all 10 elements, or maybe 5 elements out of this 10 elements to process 1, then the other process that's receiving should have space for holding 5 elements.
Okay.
Then all those 5 from process 1 will get copied to the 5 in the
So
other
some
end.
process has nothing there. And if you have like 30 elements,
30 elements.
if you want to spread around 5,
Uh-huh.
how do you divide it?
That you have to, that there are 2 things that you need to know. You have to have a vector named count, and you have to have a vector named displacement.
Okay.
So that vector named count, I'm telling you about a scatter V mode, wherein you want to have a variable amount of scattering. So you could have like something like, I'm assuming you want to say, like first 5 elements is what I want to send to one process, next 10 I want to send to other, etc., etc. Or you want to repeat the sending of certain elements to other processes. You can set all this up using the count vector and the displacement vector that you will write in your program. Now once you have set the values for these vectors, you pass those vectors as arguments to the scatter V and the gather V calls. Okay? So MPI broadcast, as I was telling you, sends a message from the process designated as root to all other processes in the group. Okay? And MPI scatter, as I was telling you, it distributes distinct messages from a single source to each task in a group. So I hope the diagram was more clear than the long explanation and the syntax here. So by now you know like what scatter does and what gather does, or what broadcast does, right? Just to distinguish between the two again, broadcast is one message and the same message going to all processes. Scatter is specific bytes going to specific processes. Okay? Then we have MPI gather, which is just the reverse of MPI scatter, and it gathers distinct messages from each task in the group to a single destination task. Then, like we have gather, we have all gather. In all gather, like I showed you with the previous diagram here, like this one, so each process is sending something to the other process. So all processes end up with the same kind of data in the end, right? So that's all gather. Now, to tell you a little bit about the collective communication, communication with computation. So there are routines like reduce that you will see in the exercises. So the reduce routine, what it does is, for example, when you are gathering the data from 10 different processes, you want to say, let's say, I want to add all the local data I got from different processes into one element, right? So I could use the reduce operation, and the combined value will get stored, okay? So here, when I do a reduce, for the reduce to work, you have to specify a rank, as to at what process number is this reduction happening, or where is the result going to get accumulated. Now, just like we have reduce, we have all reduce. When you do all reduce in place of reduce, then the combination or the accumulation of the results is copied to all the processes. Okay? That's advantage of all reduce. So to tell you about the syntax of all reduce, we have basically send buffer. We have to specify the address of the send buffer. You have to specify the address of the receive buffer. And you have to specify the count, as in how much data are we transacting, right? We need to know the data type, which I said could be primitive or the derived, right? Then you have to specify the MPI reduce operation. And the possible values, like 4 possible values, I should say, are MPI max, min, sum, and product. Like while you're gathering the values from the different processes, you could do sum operation on them, you could do multiplication, you could find the minimum of the values or the maximum, and there are many more that you can look into the documentation. Okay, these are just 4 that I mentioned here. And then you have to specify the root. By root, I mean what is the process at which the result of this computation is going to get stored at. Okay, and then you have to specify the default communicator, or maybe the communicator that you want to use, which might not be the default one. Okay, the last argument is the communicator. Now that was reduce. I told you about all reduce as well, right? When the result of the computation needs to be stored on all the processes, then you want to use MPI all reduce. Okay, and you notice that the only difference between reduce and all reduce is that this guy has 1 argument less. You don't have anything like root there. That is because whatever we are summing, or whatever we are multiplying, or whatever minimum and maximum value we find, that result is going to be shared with all the processes. So pretty much there's no point in specifying the IDs of all the processes participating in the communication. That's why we don't have a rank there. Okay. And like this, there are many more functions like reduce, scatter, all to all, scatter v, gather v, that I encourage you to explore. And that was about it. Let me quickly go to the examples. Like I have a couple of examples here in C. And the Fortran guys, as I said, you might want to be following similar examples from slide number 67 onwards. So here I'm showing you a sequential program with 1 for loop. And in this one, the loop is running from I equal to 1 to I less than up to val. The upper limit is up to val. Okay. And up to val is set to 10,000. So pretty much I'm doing the sum of first n numbers where n is 10,000. And instead of using a cute small formula, I'm just wanting to use the for loop, and the whole purpose of this example is to demonstrate how to use or how to write an MPI program. Okay. Now, this is my serial program for computing the sum of first 10,000 numbers. If I have to make it parallel, as I told you, the first thing that I want to include is the MPI header file. Then I want to have a routine for initializing the MPI environment. I want to have a routine for terminating the MPI environment. And then I might use some other routines in between and some other logic or code in between to do my computation of for loop in parallel. Okay. Now let's look at this modified version of the serial program, which is a parallel MPI program in which I show you how to use MPI reduce. Now, as I was telling you, look at line number 2. I've included MPI.h. Then at line number 5, I have extended the variable declaration section by declaring maybe 4 more variables: start, end, rank, and size. Line number 6 is same as in the serial program. At line number 7 is where I initialize the MPI environment. At line number 8 is where I calculate the size, or I find out the number of MPI processes that are participating in my communication, okay, or those that are associated with MPI COM world, right? Then I have MPI COM rank. I want to find the rank of each process, okay. Now, whatever you see from line number 10 to 15 is just the very basic maths I'm doing to find out if I want to do a linear distribution of data, if I want to say process I want to do like process 0, you take the first 100 pieces, process 2, you take the next 100 pieces, and so forth. If I want to do that kind of linear data distribution amongst the processes, that's the formula I'm using there for that. At line number 10 to 15, I say the start, where do I start computing from? Right? I have to compute the sum of 1 to 10,000, and my rank is 9. How do I know where to compute, where to start calculating? So if you put rank as 9 in this equation on line number 10, you know that up to val is 10,000. Size is how many processes there are. If you're running this with 10 processes, your size is 10 and plus 1. So you will end up with the value at which your process 9 would want to start doing the computation, and so forth for each process. Okay. You'll have the slides. You don't have to write. You're online already. And then you can do this calculation. You can say, like, if rank is equal to size minus 1, then n is equal to up to val. Like, count from the number of elements that I will have will begin at start and end at up to val, because I'm the last process in that series of ranks, right? If that is not the case, as in if I'm not the last process in the whole series, then I would want to have my end calculated as start plus up to val divided by size minus 1. So this is just the basic formula. So if you take like pen and paper and you just take like first 100 numbers, and you see like if you have 10 processes, how would you distribute the 100 numbers linearly across all the 10 processes, right? So this formula you can hand run this program and see how this formula helps you do that. So then you see here that line number 16 and 17 are unchanged as in the serial part, but at line number 18, you see the change. Earlier, let me go back to the serial version. In this version, we had the loop starting from 1 and going to up to val, right? But in this parallelized version, I have the loop starting from start and going to end. And I customized the start and end for each process by all that computation I did in the lines here, from line number 10 to 15, right? That's what I was explaining to you just now. Okay, then the rest of the stuff is as is, and I invoke MPI reduce in the end. So the sum that's computed in the for loop would just be a fraction of the total sum I want to compute. Each process is engaged in calculating a fraction of the sum that I want to combine. I want to sum up all the local sums into a global sum. That is why I'm using the MPI reduce function call here. So in this, I will pass the sum, the local sum variable, and the global sum variable in which I want to accumulate all the values of the local sums. And I tell that the number of elements I want to engage in this computation is 1. The data type is MPI int, and the type of reduction operation is MPI sum, and the rank of the process at which this reduction will take place is 0. That's why I have 0 here, and I've specified the communicator as MPI convol, okay? Then all I'm doing is printing the sum total, rank, basically through this printf statement, and I call MPI finalize at line number 23. Without even looking at the results, can you gauge what would be printed on the screen for rank, sum, and total? Rank would be each process prints its rank. Each process is going to print this message, right? Okay. What would be sum? Whatever little portion that they compute. And the sum here. Because each process is computing sum, local sum, okay? Yeah, so this sum is the local sum. And the global sum that we reduced for process 0 is sum total. So when you print this, you would see that only one of the processes printed non-zero value for sum total. And that was because we were doing the reduce operation only on process 0, okay? My rank here is 0, notice that in the reduce. So that's what my output looks like, okay? I hope that's self-explanatory now after the small explanation that I gave you. Now think about this. If you have to flip this scenario, as in instead of having the value of the reduce operation saved on just one process. If you have to have it on all processes in the communication, what would you do? Perfect, all reduce. And for all reduce, you don't need the rank, as I said. So this is precisely the exercise that you would do in the hands-on session, wherein you have a program which has MPI reduce, and you are asked to change reduce to all reduce, basically. Okay. There is another example, but I'm not sure how we are doing on time. How much time do we have?
We should probably start the lab.
About to start the lab?
Yeah.
Okay. So I think this is the last example that I have on the slides, which I'm skipping. Feel free to go through this example later. But that example just showed you how to use the broadcast operation. Okay, the broadcast function. So the slides are online. And if you do not know where to find them, please ping Jason. He can send you the link for the slides. So you can go through the example and ask me questions if you have any. So just to summarize, the key routines that I told you that you want to know for writing any MPI program are MPI init, MPI finalize, MPI com size, com rank, MPI send, and MPI receive. I would say I cannot also live without MPI W time, because oftentimes I want to benchmark my program, how fast one ran as compared to other. So this MPI W time is indispensable for me to note how much time my computation spent in a particular code region. Okay, so those are the basic 6 routine again, using which you can write pretty much any MPI program. Now, if you go to slide 62, you can find the set of routines to use for the labs. So the syntax of the routines is mentioned there, so that it's handy for you. You don't have to flip through slides. So we will be looking at, you will be using MPI W time, MPI broadcast, reduce, and all reduce. Okay? And then, in conclusion, I just want to mention that not all applications can be parallelized, right? So you have to analyze and understand the data dependencies in your application. And also note that not all application will give you improved performance. There are things like communication overkill, right? Or parallel slowdown, if you will. So if you're doing too much communication, if you're engaging too many processes on a small computation, you might end up delaying getting to the results rather than achieving the results faster. That's called parallel slowdown. And also note that the total execution time of a program depends upon the computation time, communication time, and the I/O time. So you want to optimize all the components to get the best performance. So the routines that we saw, the non-blocking routines, for example, you want to be mindful of their usage, how to use them correctly to overlap computation and communication. And there's a part called parallel I/O that I did not go into today. So there are MPI I/O routines that you could choose to do your I/O in parallel wherever it's justified. Let me qualify that part though. Okay. So that's about it. Now these are some references that you can go through at your time. And as I said, there are the examples for the Fortran part corresponding to the C part is from slide 67 and so forth. So that brings us to the end of this session, and now we will move to the labs. So there are 2 sets of slides, one set for the C programmers and the other set for the Fortran programmers, and both the slides are online. I don't think anybody here is C programmer. Is there anybody online who's Fortran programmer?
There was one on.
Maybe we can just type to them that here are the slides. You might want to follow the Fortran slides.
Yeah, they know it.
The Fortran lab slides. Okay, wonderful. Come on, come on. It doesn't want to play. It just doesn't want to play. I don't know. It's okay. Maybe we can manage with this view. So
The one in the bottom right forward next to the slide bar. Right above your volume.
right above my volume. This one
Yeah, on the left.
on the left.
Yeah, just the left of that. Is that
No. 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 Okay, we'll just live with this one. So, and it's not even progressing. It's blanking out. This is weird. Maybe let me just close this and bring this up again.
Yeah, close one.
Okay, it worked. Thank you. So the purpose of this hands-on session is to help you write your basic or the first MPI program and to compile it and to run it on Stampede. So what you will do is you will go through the exercises that are bundled up for you. You will download it from Train 00 location that I will give you on the next slide. And then you will read the program, and while you're reading the program, you will see comments inserted. So wherever there are comments, it will tell you what exactly to do in that program. And also there is some description on the slides that tell you what that exercise is meant for. So pretty much you will end up modifying the code for the exercises and embedding the MPI routines which are relevant there. So first thing that you want to do is log on to Stampede if you're not already logged in, and then copy the file named trainingmpi.tgz, this one, from the train 00 location that I specify here. So are you both logged into Stampede? Okay. So log into Stampede and follow the instruction on the slide to get the tarball and to untar it. So if you use this command tar minus xvzf ~trainingmpi.tgz. So in one step, it's going to copy the tar file to your local directory and will also extract the contents of the directory for you. And once you are done with the extraction, just switch to the directory named trainingmpi. There will be a vector named cortex and sinus. There will be C1, C2, C2
And that needs to reference it on the basis for the vector space R.
Basically, you will.
And so you're looking for the one you have.
So basically, I think you will have C1, C2, C2 minus C1, these four elements in one vector.
Yeah.
And then a vector, four sections. So if you multiply the two of them,
The basis of the diagram, so you can get a matrix of the transformation of that space.
there's an addition.
Yeah.
Okay, I hope everybody is done with extracting the files and you have switched to the directory named training MPI. Are you both done with that? It's done? Okay. Now, please note that if you registered through Exceed user portal, the allocation number that you have to use is is this one, TGTRA140011. And if you registered from the TAC through the TAC user portal, the account that you have to use is training-HPC Okay. So when you untar the tarball that I pointed you to, so there will be a script named myjob.sh in there. You open that file, myjob.sh, and wherever you see the text A-XXXXX, you just replace that with the appropriate account number. That is, if you're an Exceed user, you want to say TG-TRA and the rest of the stuff there. And if you registered through TAC user portal, you want to use training-HPC. Okay, and then in order to take advantage of the reservation that we have in place for you so that you can run your jobs quickly without waiting in the queue, you want to use the sbatch command here. You want to say sbatch minus minus reservation equal to tag dash training dash 2015 dash 05 dash 04. I'll leave the slide here so that you can copy this to the job script and modify it.
Yeah, for OpenMP, like at the close of the family feature. But there's no. No, and we'll have to, no, unless you use blocking mode of communication. In the blocking mode of communication, you cannot receive the effect that you're communicating with this communication prompt is actually there. Blocking, yeah. But it's not, I mean, if you have to write a program in the immediate send mode, or in some other send mode, so you have to really wait for other processes. Or if you are in a scenario where it will be the force of communication, and after this force of communication, you have a non-blocking connectivity, like iBroadcast, you want to have something managed like this.
sbatch command, say sbatch myjob.sh. That will submit the job to the queue, and you can watch the status of the job in the queue using the sq-u command and give your username after that. So follow this exercise. If you have any problem, just ask questions. And once you're done with it, we'll do the real programming. But we are at exercise 1 at the moment. And what I've asked here, people here in the class, to compile an example program named MPI example4.c. Once you compile that program using the command on the slide, which is MPI cc -o MPI example4 and name of the file MPI example4.c, you can run this program using myjob.sh script. I'm not sure if you got the instructions of modifying myjob.sh, and if you had not got the instructions, or because we were muted here, please ask any question you have now. So these are the steps to get the tar file from train00, SSH into Stampede using the username, right, that was provided to you or that you have. Then you have SSH username at stampede.tag.utexas.edu. And then you get the tarball from train00 and this command tar -xvzf, the whole path that you have on the screen, that you can use to copy the tar file locally and extracting the contents of it. And after you have done with this step, switch to the directory named training MPI. Okay? After you're done with this, I asked you to modify the job script that is there in the training directory. And the name of the job script is myjob.sh. So first thing that you need to modify is the account information. So wherever in the script you see a-xxxxx, replace that with the allocation that's relevant to you. If you are coming through Exceed User Portal, you might want to use TG-TRA140011. And if you're coming from the TAP User Portal, you might want to use training-HPC. Okay. In addition to modifying the job script to add the account information, you also want to add the reservation number that's there. So you can copy the whole line that's here on the slide, sbatch -- reservation equal to TAC training 2015-0504. This whole line you can copy and paste in the script right after the last sbatch directive. Okay. Now, exercise 1, as I was telling you about, was about compiling the example program named MPI example4.c that's already there in the directory. So the command to compile it is MPI cc, and you would use the modified job script to submit the program. So after the ibrun command in the job script, you have to specify the name of the executable to run, which here would be MPI example4. Okay? So in the job script, which is myjob.sh, go to the line where you see ibrun and make sure the argument after ibrun is MPI example4, the name of the executable. And once you have that, you can submit the job using sbatch command, sbatch myjob.sh. Okay, and you can monitor the status of the job by using the command sq -u and the username. I hope everyone is done with this exercise 1 and we are moving to exercise 2. So the objective of exercise 2 is to show you how to use the MPI wall clock timer. So switch to the subdirectory named exercise within the directory training MPI, okay? And do not go to the solutions directory inside exercise yet. The solutions are provided there, but do not take a peek at that yet. Just go to the file named MPI example5.c. When you open this file, you will see the commands to modify the file, modify the code in the file. So basically, whenever you see commands, you will see one comment about extending the variable declaration section. If you remember that during the lecture, I told you that the MPIW time routine, it returns double values. So if you have to use that MPI timer or MPIW time routine, then you have to have two double variables declared, two variables of type double declared in your program. You can have double T1 and double T2, right? And as you follow the commands in the program, you will see that you will see the note to begin timing a section and ending the timing of the section. That's where you will say that's where you will invoke the timing routines, MPIW time. Say T1 equal to MPIW time at the beginning and T2 equal to W time in the end, and then you can take the difference of T2 and T1 to print the time. Okay? And then you have to print this measured time using a printf call. No, just double T1 and T2.
Oh, just minus, okay.
No, double is good.
Oh,
So here you are,
we're going to get a function.
so this declaration has to be done before you use this.
Oh, yeah, here. Yeah, here.
So yeah, so you just have to take the difference.
Okay,
So you can say,
I need to declare here.
you can say or double duration equal to.
Okay.
Yeah, that's a good. Right. And you can modify the print statement there.
Yeah.
Wonderful. Are you doing good? Good. I hope everyone is done with exercise 2, but if not, please ask questions now because we're going to move to exercise 3. And in exercise 3, you will learn how to use the collective routines. So there is a program called MPI example 8.c for the C programmers, and there is a Fortran example like that for the Fortran programmers. So depending upon whether you're working in C or Fortran, pick the right file. And all you have to do is figure out where we are using MPI reduce, okay? And you know that MPI reduce is used when you have to collect the results of a computation on one process, right? And you would use MPI all reduce when you have to have that result that that you're computing while communicating on all the processes. So what I request you to do in this exercise is to change the MPI reduce call to MPI all reduce call. In order to see the syntax of MPI all reduce, you can go to slide number, well, one of the slides towards the end on the lecture slide deck. I think it's slide number 62 or 63. So there you will see the syntax of MPI all reduce. Thank you. Now moving on to exercise 4. In this exercise, the objective is to learn the usage of the MPI broadcast function. All you need to do is modify the example file named MPI example1.c if you're working on C. And for the Fortran users, please see the right file number on the slide deck. I think it's MPI 11.f, but I'm not very sure. Let me just go and see. Oh. Yeah, for Fortran, you have to go pretty much in this exercise. Like the previous exercises, there are comments inside the code. So you go to the right file and read the comments, and you will have to insert the call to MPI broadcast routine as instructed. There will be a comment around which you have to do this insertion of the MPI broadcast routine. And in order to see the syntax of the broadcast routine, you can go to the lecture slides. And once you have the broadcast inserted, compile and execute the program. The exercises are there in the directory named solutions under exercises. So even if you're not available on the chat, but we can stop the video transmission at this point. If you need more time, okay.